moving the molds. With 4 sets of molds, a gang of 8 men would curb 16 pipes per day under favorable conditions. But when the temperature was low, it was not possible to make more than 6 or 8 pipes. The pipes were allowed to stand 4 or 5 days after the removal of the mold. They could then be removed by a crane and laid in stock until used. It was found advisable to let the pipes age about 4 weeks before laying. By this time, it is stated, they would stand as much rough usage as cast iron pipe. Laying, the pipes were laid much in the same way as cast iron pipes are laid. They were each 9 ft, 9½ ins, long and weighed each about 12 cwt, and were handled by ordinary tackle. In laying, the pipes were adjusted end to end, and the joint enclosed by a temporary steel ring inside which the bitumen seal Fig. 270 was run and allowed to set when the steel ring was removed. The joint was then encircled by a collar of similar construction to the pipe itself, and the space between collar and pipe was pawed with cement mortar. About 10 lengths of pipe were laid per day by one gang of men, one jointer and his assistant making all the cement and bitumen joints as fast as the gang could lay the pipes. Chapter 52. Floor, wall, and roof work of structurally very simple character sum up the task of the constructor in reservoir and tank construction. The only intricacy involved lies in form, design, and construction for cylindrical tank work. Several examples of such work are given in this chapter, and in each the construction and handling of the forms are described. To repeat details here would serve no purpose, but one general instruction may be enunciated. No care is too great which ensures rigidity and invariable form, both in the construction of the individual form units and in the assembling of these units into the complete form. This is particularly true of cylindrical tank work, and especially high cylindrical tank work, where the forms are moved upward as the work progresses. To the designer, it may be suggested that any beauty he may gain by giving the walls of his standpipe a batter is paid in the extra cost of form work. Concreting in tank work is expensive. The reasons are 2. The work has to be done in a narrow space, commonly pretty well filled with a network of steel rods or bars. Again, the work has to be done uniformly well, not only for appearance sake, but because of the necessity of watertightness. Making a reservoir watertight is, when all things are said, the one difficult constructional task in tank work, and the contractor who accepts the task lightly courts trouble. Exceptionally good concreting is essential in tank work if watertightness is to be secured. The illustration of these general admonitions will be found in the specific examples of tank and reservoir work which follow. Small covered reservoir. The reservoir was designed to hold 75,000 gallons of water for fire purposes, as it is of a type which is certain to be frequently constructed, and as we have personal knowledge of the costs recorded, we describe the work in some detail. The specifications stipulated that the reservoir must be absolutely watertight, and that the roof should be capable of sustaining a load of 300 tons evenly distributed and a live load of 5,000 pounds. On 2 wheels. Figure 273 shows a plan, Fig. 274 a longitudinal section, Fig. 275 a transverse section, and Fig. 276 the column construction. Fig. 273. Sectional plan of 75,000-gallon reservoir, quantities of work. The excavation called for the removal of 579 ids of earth. There were 83 ids of concrete in the structure, although the plans called for less, the additional amount being used in increasing the 2 4-in walls to 6-in, and increasing the bottom and top on one end so as to give perfect drainage. The yardage was divided as follows. Ku, ids, footings 3, 5 columns 6, 8 sides 22, 6 girders 11, 0 top 20, 0 floor 19, 1 total 83, 0 fig 274. Longitudinal section of 75,000-gallon reservoir. A manhole had to be put in the top and a sump in the bottom. Several pipes also had to be placed in the concrete. None of these details is shown on the plan. The structure had to be waterproofed. Excavation. The excavation was made with pick and shovel and the material hauled away in carts, the distance to the dump being 700 ft. The top was shoveled directly into the carts while the rest was handled 2 and 3 times. When the reservoir was finished, dirt had to be filled in around the sides and puddled. Wages. The following rates of wages were paid on the job. Foreman $3, 00 carpenter 3, 50 carts and driver 3, 50 laborers 1, 50. The carpenters worked 8 hours a day and were paid time and a half for overtime. The rest worked 10 hours per day and were paid regular rates for overtime. Fig, 275. Transverse section of 75,000-gallon reservoir. Forms. Carpenters framed and erected the forms, but laborers did all the carrying for them. Laborers also tore down the forms. For the girders and columns 2-in. Boards were used, but for the sides 1-in. Boards with 3 times 4-in. Scantlings were used. The props for supporting the girder and top forms were 3 times 4. Except for columns and girders and some props, all the forming was used 3 times. The lumber cost, Fig, 276. Column construction for 75,000-gallon reservoir, 400 ft/m, at $24.9. 68,000 ft/m, at $18.144. 00, total $153. 60. This makes an average price per 1,000 ft of about $18. 30, which price we shall use in giving costs. The cost of framing and erecting the forms was $167. 27 for the sides, columns, girders, and top. In the forms for the sides, forming was only used on one side of the concrete for 2 sides, the earth bank being used for the other side of the forms, but on the other 2 sides the banks had caved in and forming was used on both sides of the wall. The cost per cubic yard for forms was lumber $2, 54 framing and erecting 2, 77 tearing down, 54 total $5. 85. This cost is for the yardage of 60, 4 on which forms were actually used. For the total yardage in the tank the cost was lumber $1, 85 framing and erecting 2, 01 tearing down, 40 total $4. 26. The common labor cost of assisting to erect the forms was 15% of the total. Nothing is allowed for foreman, for the contractor acted as his own foreman. The cost of forms per 1,000 ft for the amount of lumber purchased was lumber $18, 30 framing and erecting 19, 90 tearing down 4, 00 total $42. 20. As the lumber was used 3 times, the cost per 1,000 for all work and materials on the forms would be just 1/3 of this, namely, $14.06. Since the framing, erecting, and tearing down cost $19, 90 plus $4 or $23, 90 per m, ft/m, purchased, and since the lumber was used 3 times, the labor cost nearly $8 per m. Each time that the lumber was used. It will be noted that 8,400 ft/m were required for the 83 ku, ids of concrete or a trifle more than 100 ft/bm per cubic yard, it will be of interest to see the labor costs of forms for the various parts of the structure. For the sides, the cost of framing and erecting the forms was $4.19 per cubic yard. Of this cost, 4% was for common labor and the rest for carpenters. The tearing down cost 47 cts per cubic yard. For the columns, the erecting was $2.35, of which 1% was for common labor. The tearing down cost 47 cts. For the girders and top, the erecting cost $1.83, of which 35% was common labor. The tearing down cost 61 cts per cubic yard. A summary would show sides per cu, yd, columns per cu, yd, girders and top per cu, yd, framing and erecting $4.19, $2.35, $1.83, tearing down 47, 61, total $4.66, $2.82, $2.44. The greater cost of the columns' forms over the girders and top was due to the fact that the columns' forms were handled almost exclusively by the carpenters, and also in setting them great care and much time had to be used to get them plumb and in line. The cost of the forms for the sides was about twice as great as that for the top and girders. The reasons for this are evident. The walls had forms on both sides, while the top needed forming only underneath it. The area covered on the forms being about 2,200 sq.ft, as compared to 1,000 sq.ft. The side forms had to be set plumb and kept so. The framing was done ahead, but nearly half of the lumber in the sides was erected as the concrete was being put in place. The forms for the top were all put in place before any concreting was done on the top, and the carpenters discharged. A much larger percent of common labor could be used in placing forms for top and girders than on the sides. The props were nearly all put in place by laborers. The extra cost of tearing down the forms for the top was due to the fact that the lumber all had to be handled one piece at a time through a small manhole in the top and carried about 150 ft. To be piled. To all the costs for forming should be added 6 cts per cubic yard for nails, wire, and lines used on the forms, concrete. The mixtures varied for the different members. The cost of materials was as follows. Cement, 110 bbls at $1. 12 $123, 23 quarters in. Stone, 80 cu, ids at $1, 86 148, 80 gravel, 3 cu, ids at $1, 33 4, 00 sand, 42 cu, ids at $1, 2050. 40 the sides were first put in place, then the center columns were built, following which the bottom was placed. Then the forms were erected for the top and the girders, and these cast. In building the sides, one side and half of the two ends were built at one time, and then forms erected for the other half of the sides. For the sides, the mixing was done in the bottom of the reservoir. For the rest of the structure, it was done on the ground, the mixing board being alongside of the reservoir. The labor cost of the concrete work for the various members and the average per cubic yard was as follows. Sides, columns and footings, bottom, girders, top, average, cubic yards 22, 610, 319, 11120, 083, preparing and cleaning up $0, 166 $0, 060, $0, 095, $0, 065 handling materials 1, 022, 306 $0, 070, 198 $0, 187, 404 cleaning out forms 040, 070, 053, 032 mixing and placing 1, 542, 728, 353, 792 1, 080, 952 ramming 1, 090, 540, 455, 450, 597, 673 handling steel, 890, 020, 395, 083, 324, total $4, $751, $654 $0, $878 $2, $0002, $0002, 450. The total cost of labor was $203.35. The mixing was done entirely by hand. Some plastering was done to the walls after the forms were taken off, and the sides and bottom were washed with a brush with cement and water. The plastering cost $6.60, including a barrel of cement and the washing or grouting. 2 coats cost $9.10, including a barrel of cement. This added a cost of 19 CTS per cubic yard to the concrete work, making the total cost per cubic yard $2.65. It was a mistake to have mixed the concrete for the sides in the bottom of the reservoir, as it made 2 handlings of the materials and compelled all the concrete to be raised by hand to place it in the forms. This accounts for the high cost of these 2 items. The handling of the steel was high for the side walls, as it was all separated and put into piles for the different panels and members in getting it out of the pile for the sides. The rammers not only rammed the concrete, but they also bent down the prongs of the steel to get them in place in the narrow forms, and afterwards had to pull out these prongs. This had to be done for every piece of steel used, and readily doubled the cost of ramming. The high cost of ramming the top was caused by the fact that the 6 ends of concrete had to be placed in 3 layers and each rammed. The steel handling was high on account of the prongs entangling the pieces with others, making them hard to handle. The cost of handling steel per ton was about $4 or 0.2 CT per pound. The steel was all handled by common laborers. The stockpiles of material had to be made along a street and alley, and thus caused the material to be handled in wheelbarrow several hundred feet. The preparing to mix concrete, the cleaning up afterwards, and the cleaning out of forms are items that are seldom kept separate from the others. The cost of mixing and placing is high, owing to the fact that working space was small, and the mixers had to wait until the concrete was taken off the board and placed in the forms before starting another batch. This also meant an increased cost in the ramming, as the rammers were idle some time waiting for a new batch to be mixed. The total cost of concrete, including labor and materials, per cubic yard on a basis of the 83 IDs was per QYD. Cement 1/3 BBLS at $1, $12 1, 49 stone 1 QYD, 186 sand a half QYD, 60 steel 4, 76 forms 100 FTBM at $18, 31, 85 labor on forms 2, 41 labor on concrete and steel 2, 65, total $15. 62. The cost of a foreman is not included in this, as the contractor looked after the men himself. Waterproofing. The waterproofing of the structure proved a serious problem. It was thought at first that the concrete itself would be nearly watertight, but the tank leaked like a sieve. After considering several methods, an agent of a European waterproofing mixture prevailed upon those interested to try his compound. To apply it, the walls had to be dry, so a large coal-burning stove was put in the reservoir and a fire kept up day and night. While this drying process was going on, several light falls of snow occurred, and this had to be cleared away to make the walls and roof dry. 2 coats of the mixture were applied according to the agent's instructions, and the reservoir was tested. The water fell nearly half a foot in an hour's time. Then a waterproofing contractor agreed to make the reservoir watertight with paper and tar by applying it on the inside. 3 thicknesses of paper were laid on the bottom and run well up on the sides, each layer of paper being well covered with a preparation of tar. Upon testing it, it was found that the leaking had been reduced about 50%. A preparation of asphalt was then placed over this, but upon a 3rd test the tank still leaked. As the subcontractor had verbally agreed to make it watertight for $125, only this amount was paid him. After this last test, he refused to do any more work. After these attempts, the sides of the reservoir were exposed on the outside by excavating around it, and a 1-brick wall built up a few inches from the concrete. This space was filled in with rich cement mortar, and the ground once more filled in around the structure. This work and the materials used in it cost $1,240. Upon a 4th test, the reservoir was found to be watertight. Thus, more than a third of the cost of the entire work was in waterproofing the structure, and this made the contract a money-losing one, as this heavy cost was not anticipated. Several items of miscellaneous work are listed in the total cost of the reservoir, such as filling in and puddling around reservoir and replacing cobble paving. The top of the structure was used as a bin for the storage of coal. For this purpose, 8 I-beams were embedded in concrete around the top to be used as posts for the sides of the bin. The cost of placing these is given. Total cost. The cost of the structure without any profits was 579 ku. IDS. Excavation at $896 529. 65 steel 395. 00 crushed stone 148. 80 gravel 4. 00 sand 50. 40 cement 123. 20 lumber 153, 60 labor on forms 200, 09 labor on concrete 203, 35 plastering 6, 60 sides and bottom 9, 10 nails, wire, etc. 4, 98 baling water 21, 19 building temporary fence 1, 65 extra excavation for forms, footings, etc. 13, 90 setting I-beams in concrete 17, 65 filling in and putting around reservoir 34, 47 replacing cobble paving 4, 30 hauling tools 3, 60 heating reservoir and handling snow 14, 50 waterproof mixture 29, 00 labor applying it 9, 74 applying paper and tar, labor and materials 125, 00 labor and materials of final waterproofing 1240, 00 tools 48, 75 general expense 210, 00 total $3,602. 52 covered reservoir at Fort Meade, South Dakota. The following account of the method and cost of constructing a 500,000-gallon reservoir is compiled from information furnished by Mr. Samuel H. Lee, M. Amsock, C.E., as shown by Fig. 277. The reservoir consists of 2 equal compartments, each 50 times 60 ft, inside dimensions with rounded corners. Both compartments are covered with a 3-in slab roof carried on the walls and interior columns. The concrete was a 1 to 2 to 4 Portland cement, sand and broken stone mixture mixed by hand on a movable platform. A concrete gang consisted of 4 men who were each paid $2.75 per day. They wheeled the materials from the supply piles to the mixing platform, mixed the concrete, and deposited it in place. During the construction of the footings and floor, 2 concrete gangs were employed, but after the walls were started, 1 gang only was required for concrete work. The other gang was then put to work assisting the carpenters. Fig. 277. Reservoir at Ft. Mead, SD. The sand and stone were wheeled to the platform in iron wheelbarrows of 2½ cu. Ft. capacity. The cement was in a quarter BBL. Sacks, and each sack was taken as 1 cu. Ft. Each batch of concrete contained the following quantity of material: 2½ sacks of cement to 1/2 cu. Ft. 2 wheelbarrows of sand 5 cu. Ft. 4 wheelbarrows of stone 10 cu. Ft. The quantities of sand and stone were adjusted so as to form the proper proportion for making a dense concrete. From time to time, as the work progressed, experiments were made to determine the percentage of voids both in the sand and the crushed stone, and in this way, uniformity in composition was secured. The mixture was made quite wet in order to ensure a free flow around the reinforcing bars. On account of the narrow space inside the forms and the number of reinforcing bars therein, care was taken to cause the mixture to be well distributed throughout. The wet concrete was well spaded in an effort to secure a smooth surface next to the forms. This was generally accomplished, but some rough places which showed after the removal of the forms required patching up. In constructing the footings, some concrete was first deposited in place, and the metal reinforcement was embedded therein. For the floor reinforcement, the lower bars were carefully embedded in the concrete after it had been brought to a suitable height. The upper bars were then placed crosswise upon the lower ones and kept in position until the remainder of the concrete had been deposited around and over them. In the wall footings, a depression or groove, several inches deep, was left under the wall space for its entire length. This ensured a good bond between the wall proper and the footing. The concrete floor in each compartment was built in one continuous operation, the object being to secure a practically monolithic construction. The lower reinforcing bars in the floor were embedded at the proper depth in the fresh concrete, and the upper bars were then placed crosswise upon the lower ones. The 2 sets were then wired together at a sufficient number of places to prevent displacement, while the remaining concrete was being deposited around and over them. The reinforcement for the walls and columns was erected in place upon the footings and formed a steel skeleton around which the forms were erected. The upright bars in the walls were held together and at the proper distance apart by means of templates consisting of wooden strips in which holes were bored at suitable intervals to receive the bars. The templates were maintained in a horizontal position and were moved upward as the concrete advanced in height. The horizontal reinforcing bars were wired in place to the upright bars. They were placed in position ahead of the concreting as the wall was built up. The corrugated bars in beam and girders were placed in position in the forms and held up by blocks which were removed as the forms were filled with concrete. The expanded metal reinforcement for the roof slab was placed so as to be close to the lower face of the slab, but far enough up to be entirely enveloped in the concrete. The wall forms were made of 2-in planks, surfaced on the inner side and placed horizontally on edge. They were held in place by 4 times 4-in posts spaced at intervals of about 4 ft, in pairs on opposite sides of the wall. The posts were firmly braced on the outside. They were prevented from spreading by connecting wires passing through the wall space between the edges of adjacent planks. At the rounded corners of the reservoir, the pairs of posts were spaced about 2 feet apart, and the curve was made by springing thin boards into place to fit the curve and nailing them to the posts. The posts were high enough to reach to the top of the wall. The siding was built up one plank at a time as the concrete work progressed. Column forms were made of 2-in, planks on end, extending from floor to girder. 3 sides were enclosed, and one side was left open to receive the concrete. This side was closed up as the concreting advanced in height. The beam and girder forms were open troughs of the required dimensions, made of 2-in. Plank, surfaced on inner faces. The form of centering for the roof slab consisted of a smooth, tight floor of 2-in. Planks, extending between the open tops of column, beam, and girder forms over the entire area between enclosing walls of the reservoir. The centering and the beam and girder forms were supported by 6x 6-in. Posts resting upon the floor below. The regular carpenter gang consisted of a foreman carpenter at $5 per day, a carpenter at $3.50 per day, and 2 helpers at $2.75 per day. During the early concrete work of making footings and floor where forms were not required, the carpenter force was employed in erecting the steel skeleton for the walls. The upright bars were placed in position and secured by temporary wooden stays, extending from the upper portion of bars to the surface of ground outside of excavation. These stays were removed after concreting had advanced to a sufficient height to hold the steel securely in place. The wages paid the concrete gang which mixed and placed all the concrete and the carpenter gang which constructed and erected the forms and placed the reinforcement have been given above. The costs of construction materials on the site were: cement per barrel $2, 57 sand per cu yd, 1, 80 stone per cu yd, 3, 15 lumber per m, ft, b, m, 27, 50. The quantities in the completed concrete structure were as follows: total volume of concrete in reservoir 704, 71 cu ids. Total volume of steel reinforcement in reservoir 57 cu ids. Total volume of material in completed structure 710, 28 cu ids. The steel was therefore about 0.8%. Volume of material in structure exclusive of roof slab 648, 35 cu ids. Volume of material in roof slab 61, 93 cu ids. Total 710, 28 cu ids. The cost of the structure per cubic yard of concrete exclusive of the roof slab was as follows: item per cu yd. Crushed stone $3, 168 sand, 842 cement 3, 859 reinforcement 4, 959 labor mixing and placing concrete 1, 721 forms, labor and material 2, 960, total $17. 509. In constructing the roof slab, the expanded metal reinforcement raised the unit cost. For this portion of the work, the costs were: item per cu yd. Expanded metal reinforcement $5, 241 other items, same as above 12, 550, total $17. 791. The floor and the inside surface of reservoir walls were covered with a coating of cement mortar composed of 1 part Portland cement and 1 part sand. The wall plastering was from a 1/2 in to 3/4 in thick. It was applied in 2 coats. The floor finish was laid in alternate strips about 1 in thick and 3 ft. wide. After the strips first laid had hardened, the remaining strips were laid, the edges being grouted to ensure tight joints. The outside of walls and roof was covered with a coating of tar which was heated in an open kettle to a temperature of about 360 OF, and then applied with a brush or mop. The cost of wall and floor plastering was 4 CTS per square yard, itemized as follows: cement 26, 4 CTS, sand 2, 6 CTS, labor 15, 4 CTS. Total 44, 4 CTS. The cost of outside waterproofing was 4 CTS. Per square yard, distributed as follows: material 2, 5 CTS, labor 1, 5 CTS, total 4, 0 CTS. While some of the cost items are apparently high when compared with the cost of similar work in other places, it should be remembered that the isolated locality and the local conditions were unfavorable for low cost. Owing to the isolated location of the reservoir with respect to large markets, and also to local sources of supply, the cost of material and labor was quite high. All construction material, except some of the stone for crushing, had to be hauled over a mountain road from 3 to 4 miles to the top of the hill selected for the reservoir site. Labor was scarce and commanded a wage of $2.50 per day for ordinary work. The laborers mixing concrete were paid $2.75 per day. Another source of much relative expense was the high cost of lumber and carpenter work on the farms. On account of the thinness of the walls and roof, the cost of lumber and labor required per cubic yard of concrete was considerable. A part of the lumber was used the second time in farms, but it was found impracticable to delay the work by waiting for the concrete to harden before beginning the new portions of the walls. This lumber was sold after the completion of the work, but the salvage was inconsiderable, amounting to less than 10% of the original cost. Fig. 278. Reservoir Farms, Bloomington, Ill. Circular Reservoir, Bloomington, Ill. An open circular reinforced concrete reservoir was constructed in 1905-6 for the waterworks of Bloomington, Ill. This reservoir is 300 ft, in diameter 15 ft, deep at the circular wall and 25 ft, deep at the center of the spherical bottom. The wall construction is shown clearly by Fig. 278, and the floor is a 6-in spherical slab reinforced by a mat of a 1/4-in. Round rods placed 6 ins, on centers in both directions. The wall reinforcement is corrugated bars. Neither the wall nor the bottom has expansion joints. Concrete. The specifications required not less than 1 part Portland cement to 2 parts sand and 5 parts clean gravel, and stipulated that there should always be more than enough cement to fill the voids in the sand, more than enough mortar to fill the voids in the gravel. The proportions were varied, depending on the character of the available material, and on the location the concrete was to occupy. The stipulations regarding the minimum quantities of cement and mortar were, however, always at least fulfilled. A 1 to 3 to 4 mixture of cement, broken stone, and gravel was largely used in the footing and wall. The gravel was fine and contained 40 to 50% of sand. The broken stone was the crusher run, with the dust screened out, and the maximum-sized pieces not larger than those which would pass a 2-in screen. The mortar facing on the front face of the wall was made of 1 part cement to 4 parts fine gravel containing sand. Some gravel from the excavation was used in the concrete for the floor. This gravel was so fine that about 1/4 of it was replaced with broken stone, and the mixture made 1 to 6. Both faces of the wall were painted with a 1-to-1 mixture of cement and sand. The inner face was also painted with a 1-to-1 mixture of waterproof, star-Stettin Portland cement and sand. The sidewalk finish on the surface of the floor consisted of 1-to-1.5 mortar, mixing and handling. The concrete mixing plant was set up outside of the site of the reservoir along a side track from the railroad. The concrete materials were delivered on the side track, except some gravel from the excavation that was used. A foot portable continuous mixer was used in making the concrete for the wall footings and the wall. It was mounted so it could discharge into dump cars on a service track laid on the ground. A double hopper was built up over the mixer, one compartment for sand and one for broken stone. The end of a service track leading from the side track was laid on an inclined trestle up to a floor level with the top of this double hopper, the materials being hauled in dump cars from the side track to the hopper. The service track from the mixer extended entirely around the wall and 10 ft. From it, on the embankment made there with earth from the trench for the wall footing. The concrete was dumped from the cars on the service track to portable shoveling platforms near the point where work on the wall was in progress. It was shoveled by hand from these platforms to place in the forms, as the presence of the reinforcement bars in the narrow forms precluded dumping in large quantities. The footing was built without forms up to the right-angled joint between it and the base of the wall at the front, and to the top of the 45 degrees slope on its rear face. A layer of concrete 5 in thick was first placed in the completed trench. The reinforcement bars near the bottom were then laid on this green concrete, the vertical bars near the front face of the wall usually being erected at the same time. The concrete in the toe of the footing and in the footing proper up to the top layer of reinforcement was then laid. After the top layer of reinforcing bars had been laid, the footing was completed, except for a top layer about 2 ins, thick at the base of the front face of the wall and 15 ins, thick at the toe of the footing. This left a strip of surface about 6 ft. wide, sloping at about 1 in 6 from the wall toward the center of the reservoir, and furnished the widest and best possible bond for the joint which had to be made when floor was laid. Location and construction of forms and wall. The design of the wall of the reservoir, although simple in itself, required unusually accurate work in the location and construction of the forms for it. The location was made with very little difficulty, however, by an arrangement devised by the contractor which enabled the foreman, without the aid of an engineer, to set the necessary grade and reference stakes. A post, 10 ins, in diameter, was set very accurately and firmly in the ground at the center of the reservoir. This post was sawed off squarely on top, so that the line of collimation of an engineer's transit set on it without a tripod would be exactly at the grade of the top of the completed wall of the reservoir. A 200 ft. Steel tape was used to measure the radial distance from a nail in the center post to the posts of the back, or outside forms for the wall. In the form for the back face of the wall 2 times 6 in. Posts, spaced 1/100th of the circumference apart, were set considerably in advance of any concrete work, and were made the basis of all measurement in building the forms. The forms as originally planned are shown in Fig. 278. The wall, when started, was built continuously in both directions from the starting point. The back forms consisted of planks for lagging nailed to vertical posts, which were accurately set and firmly braced. The front forms were made in lengths equal to 1/100th of the circumference of the reservoir, and when set up were fastened to the back forms. 21 of these front form sections were built and all set up at once. Concrete was filled in between the front and back forms, starting at the central form, and was rammed in inclined layers, sloping at about 1:6, both ways towards the end forms. This method was adopted in order that the concrete might be laid continuously and without joints. The lagging of one in. Boards on the vertical portion of the sections was nailed to the vertical posts, and was carried up just ahead of the concrete filling. When the concrete had reached the top of the central one of the 21 sections of the forms, and the concrete in that section had set sufficiently, the section was broken up and removed, leaving 2 sets of 10 sections of the forms. Subsequently, the other forms could be removed in turn as desired without being broken up. As the filling-in proceeded between the 2 sets of 10 forms each, the form in each set nearest the starting point was removed, carried forward, and put in place at the other end of its set of forms. 12 men were required to take down and transport one of the front form sections. In setting up a front form, its inner toe was firmly supported by a stake driven into the ground and by the horizontal board, nailed transversely under the bottom 4 times 4 in. Horizontal stringers, which rested on the ground. The upper part of the form was then securely fastened to the 2 times 6 in posts of the back forms by temporary wooden connecting strips, which were removed as the concrete filling was carried up. The sections of the front forms were also securely tied to each other. A facing of gravel concrete, rich in cement and with no pebbles larger than a ½ in, was placed on the front face of the wall, extending from the back edges of the vertical reinforcing bars to the surface. A sheet iron plate about 8 ins, wide by 5 ft, long, was placed vertically just back of those bars. The concrete was shoveled in loose to the top of these iron plates, and then the mortar was poured in between the latter and the front face forms from buckets. The iron plates were next drawn by handles attached to them, and the mortar and concrete tamped together before either had set. In making joints, the old concrete surfaces were always brushed and wet down, and, if necessary, slushed with a grout of neat cement before new concrete was laid on them. Construction of floor. The excavation over the site of the reservoir floor was brought accurately to grade 6 ins, below the surface of the finished concrete by hand after the scoop bucket excavator had passed over. In making the excavation, the levels were given on radial lines drawn from the ends of the 10 ft. Sections of the wall to the center. A rod, on which the elevations of the subgrade at every 10 ft. From the wall to the center of the reservoir were clearly marked, was used in connection with a transit on the center post in locating the elevations of different points in the reservoir floor. By using this method, the elevations required were easily found by the foreman in charge without the assistance of an engineer. When the work approached the center, the post was removed, and the transit was placed on a portable pedestal, which was set on points of known elevation on the finished concrete. The slanting surface left on the top of the footing inside the wall formed, together with the projecting reinforcement rods, an excellent bond between the concrete of the wall and that of the floor when the latter was laid. A circular strip of the floor, 16 ft. wide, was put down next to the wall first, and the remainder of the floor was laid according to the progress of the excavation. The lower 3½ ins of the concrete was usually first spread out over an area 12 or 16 ft. square, then the reinforcement was placed, and after that the top 2 ins of concrete and a ½ in sidewalk finish surface were laid. Fig. 279. Standpipe at Haverhill, Mass. The A-quarter in. Rods in the bottom are 6 ins, on centers in both directions. They were in 12 and 16 ft. lengths and were partly woven together in mats before being placed. The rods in one direction were all laid out and woven with 4 or 5 of those in the other direction, the joints being tied with small wire. The remaining cross rods were laid after the mat had been placed. The mats were overlapped 1 ft. This method of placing proved economical and efficient, giving at the same time something permanent on which to lay the remaining concrete. Standpipe at Attleborough, Mass. The standpipe was 50 ft in diameter and 106 ft, high inside with walls 18 ins, thick at the bottom and 8 ins, thick at the top. Figure 279 shows the general arrangement of the reinforcement. Round bars of 0. 4 carbon steel were used. The bars came in 56 1/2 ft. Lengths, so that 3 lengths with laps of 30 ins made a complete ring around the tank. The concrete was a 1 to 2 to 4 mixture of 1/4 to 1/2 in. Broken stone with screenings used as portion of sand. The floor was built first, and on it was erected a tower to a height of 60 ft, and a derrick with a 40 ft. Boom was set on its top. The derrick was operated by an engine on the ground which also had a revolving gear attached. When the work had reached the top of this tower, the tower was raised to 110 ft in height and the derrick shifted to the new elevation. The forms were convex and concave sections 7 1/2 ft high and about 11 ft long. The concave or outside forms were made in 16 panels, with horizontal ribs and vertical lagging. 2 complete rings of panels were used. The panels were joined into a ring by clamps across the joints, this clamping action and the friction of the concrete holding them in place. The inside forms consisted of vertical ribs carrying horizontal lagging put in place a piece at a time as the filling proceeded. They were supported by staging from the derrick tower. The remaining plant comprised a Sturtevant roll jaw crusher feeding to screens which discharged fines below A/4 in. Into one bin, medium stone into another bin, and coarse stone into a third bin. These bins fed to the measuring hopper of a Smith mixer, which discharged into the derrick bucket. The mode of procedure was as follows. The reinforcing rings were erected to a height of 7 1/2 ft. The bars were bent by being pulled through a tire binder and around a curved template by a steam engine. The bending gave some trouble due, it was thought, to the stiffness of the high carbon steel. Vertical channels 4 ins. Deep were set with webs in radial planes or across wall at 4 points in the circumference. The flanges of these channels were punched exactly to the vertical spacing of the reinforcing rings. Through the punched holes were passed short bars on the opposite ends, of which the reinforcing rings were supported and wired. The 3 sections of rod of which each ring was composed were lapped 30 ins and connected by crossby clips. Considerable difficulty was had in holding the reinforcing rings in line by the method employed. It is stated by the engineer that a greater number than 4 channels would have been much better. The reinforcement being in place, an inside and an outside ring of forms was erected. Concreting was then carried on simultaneously from 4 points on the circumference and a ring 7 1/2 ft. High was concreted in one operation. Several facts were brought out in the concreting. Careful and conscientious spading was necessary to get a smooth, dense surface. A too wet mixture allowed the stone to settle and segregate. Care was necessary in this thin wall containing 2 rings of bars to keep the stone from wedging among and around the bars, and thus causing voids. The engineer states that for this reason the substitution of mortar for concrete in tank walls is worth considering. He estimates that in this work, costing $35,000, that the use of a 1-to-2 mortar in place of the 1-to-2-to-4 concrete would have increased the cost by $2,300, a 1-to-2 a half mortar by $1,500, and a 1-to-3 mortar by $750. It was also found that there was danger from a movement of the reinforcement in the concrete and of the forms in placing the concrete. When a ring of wall 7.5 ft high had been concreted, the reinforcement was placed as before described for another ring. The 2 rings of forms below those just filled were removed from the wall, hoisted up and set in place on top. These 2 operations of placing reinforcement and setting forms for another ring of wall took 3 days, so that the top surface of the wall to which new concrete was to be added had become hard. This hard surface was very thoroughly washed and then coated with neat cement immediately before depositing the fresh concrete. Water was admitted to the tank as the work progressed, being kept about 20 ft below the work in progress. Numerous small leaks developed, but only 2 were large enough for the water to squirt beyond the face of the wall. These leaks appeared to grow smaller as time went on. To do away with them entirely, the inside wall was plastered. The first coat of plaster was not successful in stopping the leaks, so the standpipe was emptied and replastered, 5 coats being used in the lower 20 ft. This did not serve, so resort was had to a Sylvester wash, a boiling hot solution of 12 Oz. To the gallon of water of pure olive oil castile soap was applied to the dry wall. In 24 hours this was followed with a 2 Oz. To the gallon solution of alum applied at normal temperature. 4 coats of each solution were applied, which reduced the leakage to a small amount. To do away with all leakage, another 4-coat application of Sylvester wash was used. Details of the cost of the work are not available. There were 770 ids of concrete in the walls and 185 tons of steel bars. Altogether, 3,000 Crosby clips, costing $1,100, were used. The cost of the concrete in place was about as follows. Cement per yd of concrete $4, 80 sand and stone per yd of concrete 3, 90 mixing per yd of concrete 0, 40 placing per yd of concrete 2, 20 forms per yd of concrete 2, 65 total per yd of concrete $13, 95 gas holder tank, Des Moines, Iowa. The tank was 84 ft in diameter and 21 ft 5 ins deep. It had a horizontal floor 16 ins thick 5 ft, below ground level, and a wall 21 ft, high 18 ins, thick at base and 12 ins, thick at top under coping and with alternate pilasters and piers around the outside. The concrete for the floor was a 1-to-2 a 5 2-in. Stone mixture, and the concrete for the walls was a 1-to-2-to-4 1-in. Stone mixture. The floor was constructed first with a circular channel for the wall footing, and then the wall was constructed. Piles were driven in the bottom and their heads cut to level and filled around with tamped cinders. 2 circumferential rows of posts were driven around the edge, so that a pair of posts, 1 inner and 1 outer, came on each radius through a wall pilaster or pier. These posts served primarily to carry the frames for the wall forms and secondarily for holding the forms for the circular wall footing channel as shown by the sketch Fig. 280. The floor concrete was put in diamond-shaped panels between forms, whose top edges were set to floor level. Each form was designed to make a groove in the edge of the slab so that adjacent slabs would bond with it. The concrete was wheeled to place in barrows, thoroughly tamped, roughly floated to surface, and finally given a trowel finish. Fig. 280. Forms for constructing channel for wall in reservoir floor. To construct the walls, the posts before mentioned were cut off to exact level 6 ins, above the finished floor. A bent for the wall forms was then erected on each radial pair as shown by Fig. 281. The bents were erected by hand and carefully plumbed and lined up, both radially and circumferentially. The pier and pilaster forms were then erected across wall opposite each bent as shown by Fig. 281. The forms for the wall between pilasters and piers consisted of panels 4 ft. high. Fig. 281. Frame for forms for circular reservoir wall. Fig. 282. Form panels for circular reservoir wall. A panel for the inner face of the wall is shown by Fig. 282. The panel for the outer face was similar in construction, but was, of course, concave instead of convex. Enough panels of each kind were made to reach entirely around the tank. The inside panels were bolted at the ends to the uprights of the bents. The outside panels were similarly lag-screwed to the uprights of the pier and pilaster forms. Fig. 281 shows the holes for bolts and lag screws. The spaces between ends of inside panels in front of the bents was closed by a ×6 in. Steel plate the full height of the wall. This plate was bolted to the bents and had anchor bolts every 3 ft, reaching into the wall. This anchoring of the plate to the wall permitted the diagonal bracing of the bents to be removed to allow runways to be laid on the cross pieces, since the plate held firmly the bent post to which it was bolted as indicated by Fig. 283. A complete circle of inside and outside forms was erected and filled. Then the forms were raised 3 ft. by block and tackle from cross timbers across wall between bent and pilaster form, and this depth concreted, and the forms raised again. The forms were oiled on the faces coming against the concrete. It took about half a day to raise and set a complete circle of forms. The concrete was mixed outside the tank and was wheeled up inclines and dumped onto runways laid on the cross pieces of the bents and then loaded and wheeled to place. The runway was raised to successive horizontals as the work progressed. Fig. 283. Sketch showing filler for joint between form panels. Only a few general cost figures are available. The labor for mixing and placing concrete was as follows. For floor per coup, YD, 3, 4 HRS. For walls per coup, YD, 5, 2 HRS. For cornice per coup, YD, 5, 4 HRS. The cost of unloading the reinforcing steel from cars and placing it in the structure was $7 per ton or 0.35 CT per LB. The cost of form lumber, framing, erecting, and taking down forms was 9 CTS per square foot of wall covered. Gas holder tank, New York City. The tank for the Central Union Gas Co.'s gas holder at 136th cent and low-cost Ave has an interior diameter of 189 ft and a depth of 41 ft 6 ins. The exterior wall is 42 ft 6 ins, deep 5 ft 6 ins, thick at the base and 4 ft 6 ins, thick at the top, concentric with it and 11 ft 6 in. Away is the interior wall 166 ft in external diameter and 16 ft 6 ins. High with a uniform thickness of 2 ft 6 ins. The bottom of the tank enclosed by the interior wall is a truncated cone whose base is at the level of the wall top. Fig. 284 shows the arrangement. It was specified that the diameter of this tank should not vary more than 2 ins, and that the exterior wall should not vary more than 1 in. From the vertical, The main form was a circular drum whose exterior face formed the inner face of the main wall. Its framework consisted of 40 vertical trusses or radial frames 6 ft deep and 42 ft high, set equidistant around the tank, these trusses being braced together on both edges by circumferential timbers. Radial horizontal pieces nailed across the radial frames and projecting beyond their faces carried vertical iron guide strips against which the movable panels of lagging were seated. These panels were cylindrical segments 5 ft, high and long enough to span between two radial frames or 14 ft, 11 ins. The panels were adjusted radially by wedges to give in clearance in respect to inner face of wall. Enough of them were made to form a complete circle, and they were set with 1 in clearance between vertical edges of adjacent panels to allow for swelling when wetted. Fig. 284. Section of gas holder tank, New York City. The concrete bottom of the annular space between walls was first constructed. On this floor were set 6 times 6 in times 8 ft sills for the radial frames. These were located accurately by transit. The radial frames were then set on the sills by a derrick, adjusted to exact radial position by a measuring wire swiveled to the center point of the tank and plumbed by transit. A complete circle of lagging panels was then adjusted to the frames at the bottom of the trench. For concreting, the wall was divided circumferentially into 3 sections. These sections were separately concreted to the top of the lagging panels, that is to a height of 5 ft. After the concrete had set 48 hours, the panels were hoisted 4 ft, so that their lower edges still overlapped the concrete 12 ins, and another ring of wall was concreted. This procedure was repeated until the wall was completed. The back of the wall was formed against the side of the trench where possible, and in other places against rough board lagging held in position in any convenient way. For handling the concrete, 4 equidistant panels of the form framework were converted into double-compartment elevator shafts, providing for 2 balanced cars controlled by a sheave provided with a friction brake. 3 mixers supplied concrete to these elevators. Considering a single elevator, 2 barrows of concrete were wheeled from the mixer onto the car at the top of the elevator frame. The friction brake was released, and the loaded car descended to the work, hoisting at the same time its twin car loaded with 2 empty barrows. The elevators distributed to wheeling platforms cantilevered out from the outer face of the framework and located successively 5 ft, 15 ft, 20 ft, etc., above the bottom of the trench. On these platforms, the concrete was distributed as required, the maximum wheeling distance being never over 1/8 the circumference of the tank. The concrete was mixed very wet and deposited in 6 in layers. The inner and outer surfaces of the wall were both painted with 2 coats of stiff cement grout neat, and in addition the inner surface was rubbed smooth by carborundum brick. Regarding this finishing work, Mr. Howard Bruce, engineer of construction, writes, "The scouring was done on each section of the wall immediately after the forms supporting these sections had been removed. The object was to rub this interior surface with carborundum before the surface of the concrete had taken its final set. By rubbing the concrete at this stage, and at the same time applying with a brush a coating of neat cement grout, we believe the face of the concrete was made more or less impermeable, as examination shows the pores of the concrete are very largely filled up. We have no accurate figures as to the cost per square yard of this treatment, but one can readily see that this cost would be insignificant as compared with the possible improvement of the work. The carborundum brick was selected on account of its hardness. I believe practically any stone would answer the same purpose. In addition to filling the pores of the concrete, this treatment gives the surface a good smooth finish, aligning a reservoir Quincy, Mass. The following methods and costs are given by Mr. C. M. Saville, M. Amsock, C.E., for lining the Forbes Hill Reservoir at Quincy, Mass. This reservoir is 100 times 280 ft, on the floor with side slopes of 1:1, 75, and was built by contract in 1900-1901. Fig. 285. Section of reservoir lining, Quincy, Mass. Figure 285 is a section of the concrete lining. The bottom layer for the floor was a 1 to 2 to 5 natural cement concrete, and for the sides a 1 to 2 a 6 a half Portland cement concrete. The top layer on both floor and sides was a 1 to 2 a 4 Portland cement concrete, 2½ in. Stone was the maximum size allowed in any concrete and 1½ in. The maximum allowed in the top layer. Smaller stone was used for special surface work, as noted further on. The stone was cobbles turned up in the excavation work and had to be gathered from scattered piles and washed before crushing. A 9 times 15 Farrell crusher, operated by a 12 HP. Engine did the crushing. It was rated at 125 tons a day, but averaged only about 40 tons. The fine dust was screened out and the remainder discharged into a 30 cu. YD, 3-compartment bin, 1 compartment for stone less than 1½ ins, another for 1½ to 2½ in, stone and a third for returns. The stone had 46% voids and weighed 95 pounds per cu ft. The sand was of excellent quality. Atlas and Beaches, Portland and Hoffman natural cement were used. All concrete was mixed and placed by hand. The concrete gang consisting generally of 1 sub-foreman, 2 men measuring materials, 2 men mixing mortar, 3 men turning concrete 3 times, 3 men wheeling concrete, 1 man placing concrete, and 2 men ramming concrete. 2 gangs were ordinarily employed, each mixing and placing about 20 cu. Ids per day or 43 cu. Ids per man per day. The materials, sand and stone, were measured in bottomless boxes, the following sizes being used. Sand box, stone box prop, of mix, size vol cu ft, size vol cu ft, 1 to 2 of 4h 29 times 2 times 189, 25 5 times 4 5½ 14, 8 1 to 3 to 6h 29 times 2 times 2 11, 1 5 times 6 8 22, 2 1 to 2 to 5 2 9 times 2 times 1 4 7, 4 5 times 6 6 18, 5 1 to 2 a 6 a half 2 9 times 2 times 1 8 9, 25 5 times 7 2 a half 24, 0 5h. These mixtures were used for gatehouse and standpipe foundation work. The bottom layer was placed in a continuous sheet. The top layer was laid in 10 ft. Squares on the floor and in 8 times 10 ft. Squares on the sides. These squares alternated in both directions, 1/2 being first laid and allowed to set. In laying the sides, the surface was left 1 in. Low and then before the concrete had set was brought to plane by a 1 in. Layer of 1 to 2 a 4 mixture using stone and stone dust less than in. The concrete for the floor was mixed rather wet and rammed until it quaked. On the sides a drier mixture was necessary to prevent flow. The cost of the lining concrete was as follows. Bottom layer on floor 1 to 2 to 5 mixture 1, 25 BBLS, natural cement at $1, $0.81, 350 0, 34 cu, YD, sand at $1, $0.20, 347 0, 86 cu, YD, stone at $1, 57.1, 354 a half FT. B. M. Lumber at $20 per M. 0.90 labor on forms 0. 100 labor mixing and placing 1. 170 labor general expenses 0. 0.80 total $4. 487 bottom layer on sides 1 to 2 a 6 a half mixture 1.08 BBL. Portland cement at $1. 53 $1. 652 0. 37 Ku YD. Sand at $1. 020. 377 0. 96 Ku YD. Stone at $1. 57 1. 507 lumber for forms about 1 FT/BM. At $20 0. 16 labor on forms 0. 121 labor mixing and placing 1. 213 labor general expenses 0. 177 total $5. 0.63 top layer on floor and sides 1 to 2 a 4 mixture 1. 37 BBLS. Portland cement at $1. 53 $2. 090 47 Ku YD. Sand at $1. 020 48 0. 75 Ku YD. Stone at $1. 57 1. 1712 a half FT/B. M. Form lumber at $20 per M. 0. 25 labor on forms 0. 26 labor mixing and placing 1. 530 labor general expenses 0. 150 total $5. 93 the side finish with 1 to 2 a 4 concrete of in. Stone cost $0. 154 per SQ. YD. 1 in. Thick. This work was done by a gang of 3 plasterers and 3 helpers. The layer of plaster between the concrete layers was put down on 4 FT strips and finished similarly to the surface of a granolithic walk. This layer consisted of 1 to 2 mortar finished with a 4 to 1 mortar. To keep the plaster from cracking, it was covered with strips of coarse burlap soaked in water. This precaution was not entirely successful. Some cracks appeared and had to be grouted. 3 gangs, each consisting of 1 plasterer and 1 helper, did the plastering, each gang laying about 700 SQ. IDs per day. The cost of the plaster layer was as follows: item, per 100 SQ, FT per SQ, YD, per Ku, YD. Cement at $1, 53 $1, 15 $0, 103 $7, 42 sand at $1, 020, 13 0, 012 0, 86 burlap 0, 020, 0020, 14 labor 0, 92 0, 083 6, 00, totals $2, 22 $0, $214. 42 It will be noted that it took over 5 BBLS of cement per cubic yard and that the labor cost was $6 per cubic yard. Relining a reservoir, Chelsea, Mass. The following account of relining the Powder Horn Hill Reservoir at Chelsea, Mass. is taken from a paper by Mr. C. M. Saville. This reservoir, which holds about 1 million gallons, is oval in shape, 98 times 175 FT. At the top, 68 times 148 FT. At the bottom, and 15 FT. Deep, with side slopes about 1 on 1. The work was done by day labor. For sake of completeness, the costs of excavation and backfilling are given here as well as the concrete costs. The top of the bank was too narrow to allow the use of carts and an 18-in. Gauge railroad was decided upon as most convenient for handling materials. A 65 FT, boom derrick with a 70 FT. Mast was used for removing the excavated material and for depositing concrete. The derrick was operated by a 15 P. double-drum hoisting engine was held in place by 6-wire guy ropes and had a reach such that only one moving was necessary after it was placed. The engine and derrick were set up on the floor of the reservoir, and the work of excavation was begun at about the middle of the south side. In order to facilitate the work, a platform supported on frames was set up. These frames were spaced about 15 ft, apart and rested on the bottom and slope of the reservoir, being held in place by bolts driven into the floor. The paving blocks on the top of the slope were removed and piled up to be taken away. The old lining and the material excavated from the bank were shoveled into the scale pan of the derrick, hoisted to the cars on the top of the bank, and then run by gravity to a dump a short distance down the hillside. Here the cars were run out on a rough trestle, the load dumped, and the empties hauled back to the work by a rope carried through pulleys to the winch head on the hoisting drum of the engine. For the storage of some of the materials, 2 small portable storehouses were set up, one 8 x 10 x 7 ft, the other 11 x 16 x 7 ft. The bulky portions, such as cement, sand, and stone, were delivered as necessary, a few days' supply only being kept on hand. A branch from the railroad was so arranged that it passed the storehouses and stone piles, while the sand was piled close to the concrete mixing board. The intention on the work was to do nothing by hand that could possibly be done by steam, except that all of the concrete was mixed by hand. As great a proportion of water was used as could be done without causing the material to slide when rammed in place. The lower layer of concrete was of the proportion by volume of 1 cement, 2 1/2 sand, and 6 1/2 crushed stone, sizes from 3/4 to 1 1/2 ins. This was rather a lean mixture, and as it could not be rammed enough to flush all over, the surface was finished where necessary by a thick mortar made in the proportion of 1 cement to 6 sand, and applied with heavy brushes. Before placing any of the concrete, the bank back of the old concrete left in place was thoroughly rammed with iron railroad tampers, and the edge of the old concrete was scrubbed with water and a stiff brush, and then coated with 1 to 4 grout, which was allowed to fill in the angle between the concrete and the slope. Just before placing the concrete, the earth bank was well wet in order that moisture might not be drawn from the concrete while it was soft. In order to make the new lining as waterproof as possible, a layer of asphalt was placed on top of the lower layer of concrete, and brought up on the exposed edge of the old layer at the bottom of the new work. This, it was expected, would make an elastic and watertight joint between the new and the old work. Venezuela asphalt, crystal brand, was used, being poured upon the top of the concrete layer and allowed to run down the slope, care being taken that the concrete was entirely and perfectly covered. After the first layer of asphalt was cool, a second layer was similarly applied, and the resulting sheet was about 1/4 in thick. Any inclination to crawl down the slope when exposed to the sun was readily stopped by throwing on a pailful of cold water. A most particular part of this work was to get the asphalt as hot and liquid as possible, and yet not burn it. All of the concrete was protected from the sun and kept damp by being covered with strips of burlap, which were moistened by sprinkling. The upper layer of concrete was composed of a much richer mixture of concrete than that used in the bottom layer, the proportions by volume being 1 cement, 1 1/4 sand, 1 1/4 stone dust, and 4 broken stone of the sizes mentioned above. On account of the steep slope, it was possible to do only a little ramming, and the material was laid as wet as possible. To make this layer more impervious and also to obtain a smooth surface, the concrete was left about 1 inch below and a finish coat applied by expert granolithic finishers. This coating was applied as soon as it was possible to do so after the main layer was in place, but on account of the steepness and the liability of the wet concrete to flow, care had to be taken not to begin work too soon. The top finishing coat was made in the proportion of 1 part cement, 1 2/3 part sand, and 3 1/3 parts stone dust. In order to help in bonding, the last ramming on the concrete was done with rammers studded with pieces of iron about 1 in, long and 1/2 in deep. The finishing was done in 3 operations. The material was spread on the concrete and thoroughly worked into it by the finishers, using rough wooden floats. After this, it was gone over and partially smoothed down with a thin steel float, and finally it was worked to give the finished appearance and an impervious surface. The underlayer of concrete was placed in a continuous sheet. The upper layer was put down in alternate strips, 10 ft long the whole length of the layer and 5 ft wide. These blocks were built up in forms which were not removed until the concrete had set. Finally, the back or edge of the block toward the bank was well wet and thoroughly plastered to prevent, as far as possible, the infiltration of any water. The plaster was mixed in the proportion of 1 part cement to 4 parts sand. When the forms were wholly removed, the space between the concrete and the bank was refilled to within about 6 ins of the top with a clayey material previously excavated, and the space was filled and graded to the top of the bank with loam. During the work, 2 holidays intervened. The men were also transported to and from the work. Charges were made for these items, amounting to $209.77, and this sum, together with the cost of installing the plant, $716.03, are proportionally charged against the work as follows: percent total per coup, YD, excavation 70, $3,651, $2, 17 lower concrete 12, 111 1. 16 upper concrete 15, 4 143 1, 11 backfill 2, 321, 28. The detailed cost of repairing the reservoir lining is given in the following tabulations: excavation, rate, per coup, YD. Foreman 95/9 days $4.000. 13 engineman 12/3/9 days 3.00. 12 carpenter 2 days 2.67. 02 laborers 9/6/9 days 2.25. 07 laborers 110 2/9 days 2.00. 73 laborers 46/5/9 days 1.75. 27 derrick 12/3/9 days 3.75. 15 rails and cars 11/2/9 days 0.40. 02 stove coal 3.05 tons 6.50. 07 egg coal 95 tons 6.25. 02 total 300 coup. IDS 1.60 estimated proportionate charge for plant installation and holidays 2.17 grand total 3.77 lower layer concrete rate per coup YD. Foreman 37/9 days $4.000. 16 engineer 23/9 days 3.000. 07 carpenters 7 days 2.67. 20 laborers 17/9 days 2.25. 06 laborers 89 days 2.001. 87 laborers 4 days 1.75. 07 derrick and engine 23/9 days 3.75. 08 rails and cars 22/9 days 0.40. 01 cement 106 BBLS. 1 35 1 50 San 37 4 Ku Ids 1 10 0 43 Broken Stone 117 9 Tons 1 35 1 67 Egg Coal 41 Tons 6 25 0 03 Lumber 1 3 MFT 21 000 28 Total 95 5 Ku Ids $6 43 Estimated Proportionate Charge for Plant Installation and Holidays 1 16 Grand Total $7 59 Upper Layer Concrete Rate per Ku YD Foreman 6/7/9 days $4 $000 21 Engineer 18/9 days 3 04 Carpenter 18/5/9 days 2 67 0 38 Laborers 17/9 days 2 25 0 03 Laborers 119/5/9 days 2 001 85 Derrick and Engine 18/9 days 3 75 0 05 Rails and Cars 83/9 days 0 40 0 03 Cement 176.5 BBLS 1 35 1 86 Sand 30 2 Ku Ids 1 10 0 26 Stone Dust 41 6 Tons 1 50 0 48 Broken Stone 122 8 Tons 1 35 1 28 Egg Coal 2 Tons 6 25 0 00 Lumber 4M FT 21 000 65 Burlap 300 Ids 0 04.5 10 Nails 170 pounds 0 050 03 Total 129 2 Ku Ids $7 25 Estimated Proportionate Charge for Plant Installation and Holidays 1 11 Grand Total $8 36 Back Plaster Rate per Ku YD Plasterer 3/8/9 days $5 40 $0 08 a half Plasterer 8/9 days 6 000 02 Plasterer 5/5/9 days 4 50 09 Laborers 9/3/9 days 2 25 0 08 a half Laborers 3/9 days 2 000 00 Cement 6 BBLS 1 35 0 03 Sand 3 Ku Ids 1 10 0 01 Total 262 SQ Ids 0 32 Surfacing Rate per Ku YD Plasterer 7/6/9 days $5 40 $0 09 Plasterer 2/1/9 days 6 000 03 Plasterer 9/4/9 days 4 50 09 Laborers 12/8/9 days 2 25 0 06 Laborers 2/4/9 days 2 000 01 Cement 22/4 BBLS 1 35 0 06 Sand 5 07 Ku Ids 1 10 0 02 Stone Dust 14 Tons 1 50 04 Total 460 SQ Ids $0 40 Asphalt Rate per Ku YD Foreman 1/9 days $4 $0 Asphalt Man 11 days 2 000 05 Laborer 6 days 2 000 02 a half Asphalt Kettle 11 days 1 50 03 a half Asphalt 3 9 Tons 30 000 25 Asphalt Mops 3 000 01 Total 464 SQ Ids $0 37 Backfilling Rate per Ku YD Foreman 13/9 days $4.000. 07 laborers 23/3/9 days 2.000. 62 laborers 9 days 1.75. 21 rails and cars 22/9 days 0.40. 02 loam 27/5/9 coup. Ids 1.25. 46. Total 75 coup. Ids $1.38. Estimated proportionate charge for installing plant and holidays $0. 28. Grand total $1.66. Installing plant. Total. Foreman 15 4/9 days $4.00. $61. 78. Sub-foreman 1 day 3.003. 00 engineer 8 4/9 days 3.0025. 33 carpenter 3 days 2.67 8. 00 watchman 42 days 2.0084. 00 laborers 17 4/9 days 2.25 38. 36 laborers 149 8/9 days 2.00 299. 78 double team 10 a half days 5.00 52. 50 single team 6 days 2.00 12. 00 single team 1 day 3.53. 50 teaming total 53. 00 derrick and engine 11 4/9 days 3.75 49. 92 rails and cars 8 2/9 days 0.43. 29 broken stone 7.05 tons 1.35 9. 52 egg coal 6 tons 6.25 3. 75 kerosene 30 gal 0.11 3. 30 oil 4 gal 0.25 1. 00 spikes 220 pounds 0.05 11 00 total $723. 03 The cost of the concrete work in the lower and upper layers can be still further detailed as shown below. Lower layer concrete 95 5 coup. Ids 1 to 2 a 6 a half concrete. Materials rate per coup YD. Atlas cement 1. 11 BBL $1. 35 $1. 50 sand 39 coup YD 1 10 0. 43 broken stone 97 coup YD 1 23 tons 1 35 1 66 miscellaneous plant coal etc. 1 28 labor mixing and placing $2.09 carpenter work on farms at $24.00 per m 34 total per coup YD in place $7.30 upper layer concrete 129 2 coup. Ids 1 to 1 a 1 a 4 concrete. Materials rate per coup YD. Atlas cement 1 37 BBL $1.35 $1.85 sand 24 coup YD 1 10 0 26 stone dust 25 coup YD 32 ton 1 50 0 48 broken stone 75 coup YD 96 ton 1 35 1 30 lumber 0 31 m FT 21 000 65 miscellaneous plant etc. 1 32 labor mixing and placing 1 85 carpenter work on farms at $21.00 per m 0 66 total per coup YD in place $8.37. The following approximate labor costs are also given. Transporting, erecting, and removing derrick, $260. 85. Equivalent time, foreman 6 days, engineer 4 days, laborer 85 days. Transporting, laying, and removing track, $125. 03. Equivalent time, foreman 4 days, laborer 40 days. Caring for dump and disposing of surplus by rough grading, $70. 28. Equivalent time, foreman 1 day, laborer 33 days. The total cost of the work was $3,503.66 divided up as follows: excavation $480, 79 lower layer concrete $614, 15 upper layer concrete $937, 94 back plaster $84, 73 surfacing $186, 04 asphalting $170, 94 back filling $103, 27 installing plant $716, 03 transportation and holidays $209, 77 grand total $3,503, 66 lining Jerome Park Reservoir. The bottom of the reservoir that was lined covered 250 acres, and the concrete lining was 6 inches thick. The lining was laid in alternate strips 16 ft wide between forms set to grade. The concrete was mixed in 18 ransom mixes provided with charging hoppers and mounted on trucks without boilers. Steam was supplied to the mixer engines from the boilers of the contractor's locomotives. One locomotive supplied steam for 3 or 4 mixers. Tracks were laid in parallel lines across the reservoir bottom from 150 to 200 ft apart. Sand and stone were hauled in on these tracks. The sand was dumped in stock piles at intervals. The stone was shoveled from the cars directly into the charging hopper, and the sand was delivered by wheelbarrows to the same hopper. 4 men shoveled the stone for each mixer. To deliver the concrete from the mixer to the work required 6 men with wheelbarrows. 2 men leveled off the concrete discharged by the barrows, and 2 other men floated the surface by means of a straightedge spanning the 16 ft strips and riding on the forms. By using a wet but not sloppy concrete and moving the straightedge back and forth, a good surface was secured. The gang mixing and placing consisted of 20 men for each mixer, and 18 gangs laid approximately 1.5 acres per 10-hour day. The gang organization and wages were as follows. Item, per 10 hours. 4 men shoveling stone at $1, $50 6. 002 men wheeling sand at $1, 53. 002 men delivering cement at $1, 53. 001 man dumping mixer at $1, 51. 51 man tending engine and water at $1, 51. 56 men wheeling concrete at $1, 59. 002 men spreading concrete at $1, 53. 002 men leveling concrete at $1, 53. 001 foreman 3. 00 total per day $33. 00. These costs do not include the fraction of a day's labor for firemen or the cost of fuel. Reservoir floor, Canton, Ill. The following costs are given by Mr. G. W. Chandler for lining the bottom of a 160 times 80 ft reservoir with corners of 20 ft, radius and vertical brick sidewalls. A 1:3 7 half-crushed stone concrete was used. It was mixed by hand in batches of 2, 7 cu ft. Cement, 9 cu ft. Sand and 20 1/4 cu ft. Stone. The sand and stone were measured separately, the sand and cement mixed dry, then shoveled into a pile with the rock well wetted, shoveled over again, and then shoveled into wheelbarrows. The stone had 40% voids and the sand 30% voids. The lining was 10 inches thick, including a 3/4 in. Coat of 1 to 2 1/4 mortar spread and worked smooth with a trowel. The cost per cubic yard of the lining in place was as follows. 0. 856 bbl. Cement at $2, $52, $14.10. 1 boo. Sand 100 pounds per boo. At 5¾ CTS 0, 58 0, 857 QYD stone at $2, 17 86 labor mixing and placing at 19 CTS, per HR 0, 80, total $5, 38 reservoir floor Pittsburgh PA. The following methods and costs of laying a reservoir floor are given by Mr. Emil Lowe, M. Amsock, C.E., for the Hilland Reservoir constructed at Pittsburgh PA in 1884 by contract. There were 7,681 ids of concrete in the floor, which was 5 ins thick and laid on a clay puddle foundation. Natural cement costing $1.35 per barrel was used. The broken stone varied in weight from 147 to 152 pounds per ft. It was quarried and hauled 20 miles by rail and then unloaded into small cars and hauled a half-mile to the reservoir. The cost of the stone per cubic yard delivered was quarrying per QYD, $0, 45 breaking per QYD, 0, 35 transporting per QYD, 0. 50 total $1.30. The sand was obtained on the site at the cost of excavation, or 1¼ CTS, per bushel. The method of proportioning and mixing the concrete was as follows: platforms 10 × 16 ft of 2 in. Plank were laid on the puddle foundation, and by these were set 5 × 4 × 1½ ft. Boxes on legs. Into these boxes 1 bbl of cement and 2 bbls of sand were emptied and thoroughly mixed dry, then mixed with water to a thin grout. 5 barrels of stone were placed on the platform and thoroughly wetted. The grout was then emptied over the stone and the two turned over 3 times with shovels. The concrete was rammed until the mortar flushed to the surface. The following costs cover various periods as follows: 2 days' work, 101 ids, total, per QYD, 27 laborers, 2 days at $1, $25.72, $90, 72.17 1 foreman, 2 days at $2, 55.000, 0495, total $77, $90, 77.12 1 month's work, 1,302 ids. 642 days laborers at $1, $35, 866, $70, 66.49 17 days water boy at $0, 60.10 20 0078 22 days foreman at $2, 50.55 000 0421, total $931, $90, 71.48 2 days work, 101 ids, total, per QYD, 27 laborers, 2 days at $1, $25.72, $90, 72.17 1 foreman, 2 days at $2, 55.000, 0495, total $77, $90, 77.12 1 month's work, 1,302 ids. 642 days laborers at $1, $35, 866, $70, 66.49 17 days water boy at $0, 60.10 20 0078 22 days foreman at $2, 50.55 000 0421, total $931, $90, 71.48 total work, 7,861 ids. Quarrying stone $0, 45 transporting stone 0, 50 breaking stone 0, 35 1/1/3 bbl, natural cement 1, 88 bu, sand 0, 10 water 0, 05 labor mixing and laying at $1, 25 0, 75 incidentals 0, 05 total $4. 05 the contract price was $6 per coup. YD. Fig 286. Form for constructing silo, constructing a silo. The form construction shown in Fig 286 was employed in building a silo 28 ft, high 22 ft, 3 ins, interior diameter and having 6 in walls. The bottom of the silo was made 9 ins, thick and set 2 ft, below the surface. The reinforcement consisted of 10 2x3/16 in rings spaced equally in the lower half and of woven wire fencing in the upper half. The iron rings were hoops removed from an old wooden silo. The concrete was a 1:6 mixture of Portland cement and sandy gravel. Figure 286 is a section through the forms. There were 20 T-shaped posts which extended perpendicularly from the ground to a height of 28 ft, being secured at top and bottom by a system of guy ropes and posts. The rings, of which there are 4, 2 inside and 2 outside, were built of weather boards with their edges reversed. 4 thicknesses of board were used in each ring. The curbing consisted of 2 times 8 tin, sticks 4 ft long, wedges driven between the vertical posts, and the rings held the latter in place. When the forms were to be removed, the wedges were knocked out and the rings sprung enough to permit the removal of the curbing. The rings were then pushed up and fastened in place for another section. The average rate of progress was 1/4 ft section per day. The forms were filled in the afternoon and moved up the following forenoon. 5-foot sections could have been built just as readily. The work was all done by farm laborers hired by the month, and 100 man-days of such labor were required, excluding 7 days' work of a mason brushing and troweling the surface. The cost of the work, not including the old hoop iron or the old lumber used in forms, was as follows. Item. Total, per coup, YD. Cement $100, $002, 62 gravel and sand 35, 000, 92 120 rod roll of fencing 5, 20 0, 01 new lumber 18, 000, 47 100 days labor at $1, 75 175, 004, 67 days mason troweling at $3, 50 24, 50 0, 64, total 38, 2 coup, ids, $357, $79, 26. The external area of the silo is 1950 SQ, FT, which makes the cost of brushing and troweling 1/4 CTS. Per SQ, FT. There were about 2,300 ft/m of lumber used in the forms, or about 61 ft/m per coup YD of concrete, groined arch reservoir roof. The following data are given by Mr. Allen Hazen and Mr. William B. Fuller in Trans. Amsoc, C.E. 1904. The concrete was mixed in 5 ft. Cubical mixes in batches of 6 coup ids at the rate of 200 coup ids per mix a day. 1 barrel of cement 380 pounds, net assumed to be 8 coup ft, was mixed with 3 volumes of sand weighing 90 pounds per coup ft, and 5 volumes of gravel weighing 100 pounds per coup ft, and having 40% voids on the average 26 BBLS of cement were required per coup YD. The conveying plant consisted of 2 trestles, each 900 ft, long 730 ft, apart, supporting 4 cableways. The cables were attached to carriages which ran on I-beams on the top of the trestles. Rope drives were used to shift the cableways along the trestle. 3-ton loads were handled in each skip. The installation of this plant was slow, and its carrying capacity was less than expected. It was found best to deliver the skips of concrete to the cableway on small railway track, although the original plan had been to move the cableways horizontally along the trestle at the same time that the skip was traveling. The cost of mixing and placing the concrete was as follows: per coup, YD, measuring, mixing, and loading $0. 20. Transporting by rail and cables 0. 12. Laying and tamping floors and walls including setting forms 0. 22. Total $0. 54. The cost of laying and tamping the concrete on the vaulting was 14 CTS. Per coup, YD. The vaulting is a groined arch 6 ins, thick at the crown and 2½ FT, thick at the piers. The lumber of the centering for the vaulting was spruce for the ribs and posts and 1 in. Hemlock for the lagging. The centering was all cut by machinery, the ribs put together to a template and the lagging sawed to proper bevels and lengths. The centers were made so that they could be taken down in sections and used again. The cost of centering was as follows: labor on centers covering 62,560 SQ. FT, foreman 435 HRS. At 35 CTS, $152. 25 carpenters, 4,873 HRS. At 22½ CTS, 1,096. 42 laborers, 3,447 HRS. At 15 CTS, 517. 05 painters, 577 HRS. At 15 CTS, 86. 55 teaming, 324 HRS. At 40 CTS, 121. 60 total labor building centers, 313 M. At $6. 37 $1,973. 87 materials for centers covering 62,560 SQ. FT. 313,000 FT, B. M. Lumber at $18, $25,700, 3,700 pounds. Nails at 3 CTS, 111, 008 BBLS. Tar at $3.24, 00. Total $5,835. 00. These centers covered 2 filters, each having an area of 121 1 times 258 FT. There were 6 more filters of the same size, for which the same centers were used. The cost of taking down, moving, and putting up these centers, 313 M. 3 times was as follows: foreman 2,359 HRS. At 35 CTS, $825. 65 carpenters, 12,766 HRS. At 22½ CTS, 2,872. 35 laborers, 24,062 HRS. At 15 CTS, 3,609. 30 team, 430 HRS. At 40 CTS, 172. 00 3,000 FT. B. M. Lumber at $20.60. 00 3,000 pounds. Nails at 3 CTS. 90. 00. Total cost of moving centers to cover 196,660 SQ. FT. $7,629, 30 Fig, 287. Forms for constructing grain elevator bins. The cost of moving the centers each time was $8, 10 per M, showing that they were practically rebuilt. For the first building of the centers, as above shown, cost only $6, 37 per M. In other words, the centers were not designed so as to be moved in sections as they should have been. Although the centers were used 4 times in all, the lumber was in fit condition for further use. The cost of the labor and lumber for the building and moving of these centers for the 8 filter beds, having a total area of 259,220 SQ, FT, was $15,438 or 6 CTS per SQ, FT, grain elevator bins. In constructing cylindrical bins 30 FT in diameter and 90 FT. High for a grain elevator, the forms shown by Fig. 287 were used. For the inside wall, a complete ring of lagging 4 FT. High nailed to circular horizontal ribs of 2 times 8 planks was used. For the outside wall, 2, 3 or 4 segments fitting the clear spaces between adjoining tanks were used, these panel segments being also 4 FT. High. The inside and outside rings were held together by yokes constructed as shown, and bolted to the inner and outer ribs. A staging built up inside the tank carried jack screws, on which were seated the inner legs of the yokes. Chapter 53. The safest rule for ornamental work is to leave its construction to those who make a specialty of such work. This is perfectly practicable in most concrete structures having ornament. Bridge railings can be and usually are made up of separately molded posts, balusters, bases, and rail. Ornamental columns in building work, keystones, medallions, brackets, dentils, rosettes, and cornice courses can be similarly molded and placed in the structure as the monolithic work reaches the proper points. The general constructor, therefore, can readily delegate these special parts of his concrete bridge or building to specialists at frequently less cost to himself, and nearly always with greater certainty of good results, than if he installed molds and organized a trained gang for doing the work. Good concrete ornament is not alone a matter of good design. It is also a matter of skilled construction. Nearly anyone can mold an ornament, but few can mold an ornament which is durable. To produce clean, sharp lines and arises which will endure, the molder must have special knowledge and familiarity with the action of cement and of concrete mixtures, both in molding and on exposure to the elements. This is knowledge that the general concrete worker rarely possesses, but which the ornament molder does possess if he knows his business. Special work is always best left to the specialist, while the more intricate ornamental work is best done by subcontract. So far at least as the actual molding of the ornaments is concerned, there is a large amount of simple paneling and molding which the general practitioner not only can do but must do. Knowledge of the best methods of doing such work is essential, and it is also essential that the constructor should know in a general way of the special methods of molding intricate ornaments. Separately molded ornaments. The cement for ornamental work must be strong and absolutely sound. Where an especially light color is wished, a light-colored cement is desirable. So-called white cements are now being manufactured. Lafarge cement, a light-colored, non-staining cement made in France, gives excellent results. Of American cements, vulcanite cement has a light color, and next to it in this respect comes Whitehall cement. A light-colored ornament can, however, be secured with any cement by using white sand or marble or other white stone screenings. Some authorities advocate this method of securing light-colored blocks as always cheaper and usually superior to the use of special cements. The choice between the two methods will be governed by the results sought. Whereas nearly as possible a pure white is desired, it stands to reason that a white or nearly white cement will give the better results. In the matter of sand and aggregate for ornamental work, the kinds used will ordinarily be the kinds that are available. They must conform in quality to the standard requirements of such materials for concrete work. Where special colors or tints are wanted, they can be secured by using for sand and aggregate screenings from stones of the required color. This is in all respects the best method of securing colored blocks, as the color will not fade and the concrete is not weakened. A great variety of pigments are made for coloring concrete. These colors all fade in time, and with few exceptions, they all weaken the concrete. The mixtures used in ornamental work will depend upon the detail of the ornament and upon whether color is or is not required. Generally, a rich mixture of cement and sand or fine stone screenings will be used for the surface and will be backed with the ordinary concrete mixture. A surface mixture of fine material is necessary where clear, sharp lines and edges or corners are demanded. The molds used for ornament are wooden molds, iron molds, sand molds, and plaster of Paris and special molds. Each kind has its field of usefulness and its advantages over the others. They will be considered briefly in the order named. Wooden molds. Wooden molds are perhaps the best for general work where plain shapes and not too delicate ornamentation are wanted. They give the best results only with a quite dry and rather coarse-grained surface mixture. If a wet mixture is used, such water as flushes to the surface cannot escape, and small pits and holes are formed, which necessitates grout or other finishing. The following are examples of wooden mold work. In constructing a 5-span reinforced concrete arch bridge at Grand Rapids, Mich. In 1904, the railings and ornamental parts of the bridge, such as keystones, brackets, consoles, dentiles, and panels, were cast in molds and set in place much as cut stone would be. Special molds were employed for each of these different shapes. These molds were plastered with an earth-damp mortar composed of 1 part cement and 2½ parts fine sand, which was followed up with a backing of wet concrete composed of 1 part cement, 2 parts sand, and 3 parts broken stone, passing a 3/4 in. Ring. The facing mortar was made 1½ inch thick. The castings cannot be told from dressed stone at a few feet distance. The part elevation and sections in the drawings of Fig. 288 show the arrangement of the various castings to form the completed railing, coping, etc. To specify is the arch ring, B the brackets, C the coping, and D, E, F respectively the base, balusters, and rail of the bridge railing. The blocks G and H show the keystone and railing post. The forms or molds for each of these parts are shown by the other drawings of Fig. 288. A description of each of these forms follows. The keystones were molded in wooden forms consisting of 1 piece A forming the top and front, of 2 side pieces F, of a bottom consisting of 2 parts B and C, and of a back piece G. The back and side pieces are stiffened with 2 times 3½ in. Pieces and the front, sides, and back are held together by yokes or clamps. The front of the mold was the only portion calling for particular work, and this was made of boards laminated together. The bracket molds consisted of 2 side pieces provided with grooves for receiving the front and back pieces, and with slots for tie rods clamping the whole mold together. It will be noted also that the side pieces had nailed to them inside a beveled strip to form a groove in each side of the cast block. The purpose of this groove was to provide a bond to hold the bracket more firmly in the adjoining concrete of the wall. The bottom of the mold was formed by a 2-in plank, and when the concrete had been tamped in place, the forms were removed, and the bracket was left on the bottom to set. It may be noted here that a goodly number of the brackets showed a crack at the joint marked X caused by tamping at the point Y. In construction, the bracket castings were set at proper intervals on the spandrel walls, which had been completed up to the level of the line XY. The coping course was then built up around the bracket blocks to the level of the bottom of the railing base. Fig. 288. Molds for railings and ornaments for concrete arch bridge. The mold or form for the coping course was designed to build the coping in successive sections and was built up around the bracket blocks and supported from the centers as shown by the drawings. To form the expansion joints in the coping course, they were inserted across the mold at proper intervals a short iron plate 1/4 in. Thick, cut to fit. The cutting of this plate was found to be a slow operation. The forms for the base of the railing, section D, consisted of 1¾ in. Stock for the sides and 3/4 in. Stock for the slopes. They extended across the arch and were held together by a very simple though very efficient clamp. This consisted of two 2x3x33 in. Pieces nailed to a 2x3x17 in. Piece by means of galvanized iron strips. About halfway down the long pieces or a 1/2 in. Rod was run through and secured up against blocks H placed about 56 ins apart. These blocks were removed as the concrete was put in place. It will be noticed from the cross-section of the railing that the balusters are set into sockets formed in the top of the base course. These sockets were formed by means of the mold shown at W and Z. In casting the balusters, section E, in. Cast iron mold consisting of 4 iron sides and an iron top was used. Originally, there were 2 end plates of iron, but it was found more convenient to have the bottom one of wood and allow the cast spindle to stand and set. The mold was held together by a 1/2 in. Bolts. It would have been more practical to have had the side casting composed of 2 parts. The form for the railing is built up around the tops of the spindles. The bottom piece is 1x9 ins, to which 4¼ in. OG molding is nailed. The sides are of 1 in, stock, and are clamped together. The top is finished off with a trowel. The mold for the posts is made in 4 parts, which fit together at the top and bottom by a bevel joint, as shown in the 1/4 section. The broad sides rest against the narrow ones and are held against the same by means of a 1/2 in. Rods running through 2x3 in. Stock, 2 in. Projections of the broad sides facilitate the removal of the form from the completed post. Fig. 289. Molds for ornamental railing posts for concrete facade for bridge. In constructing a concrete facade for a plate girder bridge at St. Louis, Mo, the railing above the base was constructed of separately molded blocks as follows. The balusters were cast in plaster molds. To make these molds a box square in plan, and the height of the baluster was constructed of wood and cut vertically into 3 sections. The inside lateral dimensions of this box were made 6 ins, greater than the largest dimension of the baluster. A full-size wooden pattern of the baluster was set up, and the 3 sections of the box were set around it. Sheets of thin galvanized metal, with their inner edges cut to conform to the curves of the baluster, were inserted in the joints of the assembled box so as to divide the vacant space between the pattern and the box into vertical sections. Fig. 290. Railing for arch bridge. Fig. 291. Form for lattice panels shown by Fig. 290. A mixture of 1 part Portland cement and 1 part plaster of Paris made wet was then poured around the pattern until the box was filled. When this mixture had become hard, the box was taken down, leaving a plaster and cement casing separated into 3 parts by the sheets of galvanized metal. This casing was separated from the pattern and given a coat of shellac on the inside. 4 or 5 molds of this description were cast. To cast a baluster, the sections were assembled and are a 1/2 in. corrugated bar was set vertically in the center. A mixture of 1 part Portland cement and 3 parts sand was then poured into the mold and allowed to harden. The molds for the urns on the railing post and the balls on the end posts were made in exactly the same manner as the baluster molds. The construction of the railing posts is shown by the drawings of Fig. 289. Referring first to the end posts, it will be seen that they were molded in place in 7 sections marked A, B, C, D, E, F, and G. The construction of the mold for each section is shown by the correspondingly lettered detail. The intermediate posts were built up of the separately molded pieces I, K, and H. The costs of molding the several parts were balusters 60 CTS, each handrail 40 CTS per lin, FT. The 6 intermediate posts cost $12 each, and the 4 end or newel posts cost $75 each. Fig. 292. Form for handrail shown by Fig. 290. In constructing the 72 FT. Span-ribbed arch bridge over Deer Park Gorge near La Salle, Ill. A hand railing of the design shown by Fig. 290 was used. In constructing this railing, the posts were molded in place, but the open work panels between posts and the handrail proper were molded separately and set in place between the posts as indicated. For molding the panels, a number of boxes constructed as shown by Fig. 291 were used. These were simple rectangular boxes on the bottom boards of which were nailed blocks of the proper shape and in the proper position to form the openings in the railing. The bottom of the form was first plastered with mortar, then the concrete was filled in and plastered on top. As soon as the concrete had begun to set, the blocks were removed so that final setting could take place without danger of cracking. When the concrete had set so that the panel could be safely handled, it was removed from the form and stored until wanted. The handrail for each side was molded in 2 pieces in forms constructed as shown by Fig. 292. The total cost of the railing in place was about $2 per lineal foot. The concrete was a 1 to 2 to 4 mixture of screenings and in. Broken stone. Iron molds. Iron molds have the same disadvantages as wooden molds in the use of wet mixtures. They can be made to mold more intricate ornaments, and in the matter of durability are, of course, far superior to wood. Iron molds can be ordered cast to pattern in any well-equipped foundry. Many firms making block machines also make standard column, baluster, ball and base, cornice and base molds of various sizes and patterns. These molds are made in 2, 3 or more sections which can be quickly locked together and taken apart. A column mold, for example, will consist of a mold for the base, another for the shaft, and a third for the capital, each in collapsible sections. Where the pattern of the shaft changes in its height, 2 shaft molds are commonly used, 1 for each pattern. Prices of iron molds are subject to variation, but the following are representative figures. Plain baluster molds 14 to 18 ins. High $7, 50 to $10 each. Fluted square balusters 14 to 18 ins. High $10 each. Ball and base 10 to 18 in. Balls $15 to $25 each. Fluted Grecian column, base, capital, and 1 shaft molds $30. Renaissance column, base, capital, and 2 shaft molds $45. Sand molding. Molding concrete ornaments in sand is in all respects like molding iron castings in a foundry. Sand molding gives perhaps the handsomest ornament of any kind of molding process, the surface texture and detail of the block being especially fine. It is, however, a more expensive process than molding in wooden or iron molds, since a separate mold must be made for each piece molded. The process was first employed and patented in 1899 by Mr. C. W. Stevens of Harvey, Ill., and for this reason it is often called the Stevens process. Sand-molded ornaments and blocks are made by a number of firms to order to any pattern. The process as employed at the works of the Roman Stone Co. of Toronto, Ont, is as follows. The stone employed for aggregate is a hard, coarse, crystalline limestone of a light gray color, being practically 97%. Calcium carbonate, with a small percentage of iron, aluminium, and magnesia. Nothing but carefully selected quarry clippings are used, and these are crushed and ground at the factory and carefully screened into 3 sizes, the largest about the size of a kernel of corn. Daily granulometric tests are made of the crusher output to regulate the amount of each size got from the machines. It has been found that next in importance to properly graded aggregates is the gauging of the amount of water used in the mixture. This is done by an automatically filled tank into which lead both hot and cold water, and in which is fixed a thermometer to properly regulate the temperature. In gauging the mix, about 20% of water is used. But of course, when the cast is made, the surplus is immediately drawn off into the sand, where it is retained and serves as a wet blanket to protect the cast and supply it with the proper amount of water during crystallization. Experiments seem to indicate that about 15% by weight gives the greatest amount of strength of mortar at the age of 6 months. While giving less strength at shorter time tests than mortar gauged with a smaller percentage of water. The method of handling the mix and casting is quite simple and almost identical with the practice in iron foundries. The mixture is made in a batch mixer to about the same consistency as molasses, from which it is poured into a mechanical agitator and carried about the foundry by a traveling crane. This agitator is so constructed that it keeps the materials in motion constantly and prevents their segregation. In each cast is inserted the proper reinforcing rods, lifting hooks and tie rods, and the casts are allowed to remain for a proper period in the wet sand after they are poured. They are then taken to the seasoning room, which is kept at as constant a temperature as it is practical to maintain. Each cast is marked with the number which determines its location in the building and the date it was cast, and it is then kept in the storage shed a fixed time before shipping. Records are kept of each cast made, and the company is able to get, as in mills rolling structural steel, the exact number and location of all casts made from the same mix. Careful records are always kept of the tests of cement and material, and test cubes are made from each consignment of cement so tested. In this way, all danger of defective stone through inferior cement is eliminated. The patterns used in making the molds and the method of molding are quite similar to ordinary iron foundry practice, except that the sand used is of special nature. The finish of the stone is generally tooled finish molded in the sand, the different textures of natural stone being produced by the veneering of the pattern with thin strips of wood which are run through a machine producing the different finishes. Each stone is provided with setting hooks cast in the blocks, which take the place of the ordinary Lewis holes used in cut stone. Plaster molds. Plaster of Paris molds are made from clay, gelatin, or other patterns in the usual manner adopted by sculptors. They are particularly adapted to fine line and undercut ornaments. The concrete is poured into the plaster mold, and after the cement has become hard, the plaster is broken or chiseled away, leaving the concrete exposed. Two examples of excellent work in intricate concrete ornaments are furnished by the Powerhouse for the Sanitary District of Chicago and by the State Normal School Building at Kearney, Neb. In the Powerhouse, the ornamental work consisted of molded cornices, cornice work, and particularly of heavy capitals for pilasters. These capitals were very heavy, being 7½ ft, long and of the Ionic design. These were made from plaster molds, made so as to be taken apart or knocked down and to release in this way perfectly. There were also scrolls, keystones, and arches in curved design over all of the 40 windows. None of this ornament was true undercut work. In building the normal school building, Corinthian capitals in quarters, halves, corners, and full rounds were made in plaster molds. There were some 30 of these capitals. They were made in solid plaster molds, the molds having been cast in gelatine molds, one for each capital. Into these the concrete was tamped, made very wet, and after the concrete had hardened, the plaster cast was chiseled away. This was very easily accomplished. These capitals were true Corinthians, having all the floreation, and undercut usually seen in such capitals. Ornaments molded in place. Molding ornaments in place is usually, and generally should be, confined to belt cornices, copings, and plain panels. Relief work like keystones, scrolls, or rosettes can be molded in place if desired by setting plaster molds in the wooden forms at the proper points. This method is often advantageous in bridge work, where comparatively few ornaments are required, such as keystones. Fig. 293. Spandrel wall mold for arch bridge. The construction of forms for ornamental work in place is best described by taking specific examples. Figure 293 shows the face form for the arch ring, spandrel wall and cornice or coping course of the Big Muddy River Bridge on the Illinois Central The section is taken near the crown of the arch. The lagging only is shown. This was, of course, backed with studding. The point to be noted in this form is the avoidance of any approach to undercut work. There are, in fact, very few straight-cut details. This brings up a point that must be carefully watched if trouble is to be avoided, namely, the construction of the form work in sections which can be removed without fracturing the ornament. To illustrate by an assumed example, supposing it is required to mold the wall and cornice shown by Fig. 294. It is clear that if the backing studs are in single pieces, notched as shown, the forms cannot be removed without fracturing at least the corner A. If the studs and lagging be constructed in two parts, separated along the line of B, the form is possible of removal if great care is used without damage to the concrete. The construction shown by this sketch does not greatly exaggerate matters. Figure 295 shows a wall form that has been given several times as a presumably good example in which, as will be seen, it is impossible to remove the board A without breaking the concrete, even if the narrow face were not broken by the swelling of the lumber before ever it became time to take down the forms. Fig. 294. Diagram illustrating details of mold construction. Fig. 295. Example of poor wall form construction. This matter of making provision for the swelling of the forms is another point to be watched. Referring again to Fig. 294, it will be seen that the swelling of the lagging, even if the cornice, instead of being undercut were straight cut on the line CD, is liable so to crowd the lagging into the corner, and B that the concrete is cracked along the lines EF or GH. A suggested remedy for this danger is shown by Fig. 296. At a distance of every 3 or 4 ft. Insert a narrow piece of lagging, and behind these lagging strips cut notches be in the studs. When the concrete has got its initial set, pull back the lagging strip into the notches B, leaving an open joint to provide for expansion due to swelling. Fig. 296. Notch studding for removal of lagging board to permit swelling. Fig. 297. Form for concrete facade shown by Fig. 298. Fig. 298. Concrete facade for plate girder bridge, Fig. 299. Forms for curved concrete abutments, Fig. 300. Cornice form, Fig. 301. Method of supporting cornice form shown by Fig. 300. In constructing a concrete facade for a plate girder bridge at St. Louis, Mo., the form shown by Fig. 297 was used. The completed facade is shown by Fig. 298. The ceiling slab was first built and allowed to set, and then the forms were erected for the frieze and coping. After these were molded, the forms were continued upward as shown for the base of the railing. Above this point, the several parts were separately molded as shown by Fig. 285 previously described. Molded in this manner, the ceiling cost 25 CTS per SQ FT. The frieze and coping cost $2 per lin FT, and the railing base cost 45 CTS per lin FT. In constructing the concrete abutments of this same structure, use was made of the forms shown by Fig. 299. These abutments had curved wing walls, and for molding, these girts cut to the radii of the curves were fastened to the studs, and vertical lagging was nailed to the girts. All the lagging was tongue and groove stuff. Fig. 302. Cornice and balustrade for arch bridge. In constructing an open spandrel arch bridge at St. Paul, Min., the cornice form shown by Fig. 300, supported as shown by Fig. 301 was used. The particular feature of this form was the use of a lath and plaster lining to the lagging. This lining was used for all exposed surfaces of the bridge. So-called patent lath consisting of boards with parallel dovetail grooves and ridges was used. This was plastered with cement mortar, and the concrete was deposited directly against the plaster after smearing the plaster surface with boiled linseed oil. This lining is stated to have given an excellent surface finish to the concrete. It cost 55 CTS per SQ FT for materials and labor. A section of the balustrade and cornice is shown by Fig. 302. The posts, balusters, and railing were molded separately. The balusters were molded in zinc molds. At first, some trouble was had in getting good casts on account of air pockets. This was largely done away with by filling the mold as compactly as possible, and then driving a 3/4 in. Iron rod through the center vertically. This rod crowded the concrete into all parts of the mold and also served to strengthen the baluster. The baluster molds were made in 2 parts. This proved a mistake. 3 parts would have been better. Chapter 54. The following cost data comprise such miscellaneous items as do not properly come in the preceding chapters. They are given not as including all the miscellaneous purposes for which concrete is used, but as being such items of costs as were secured in collecting the more important data given in preceding sections. Fig. 303. Device for drilling green concrete. Drilling and blasting concrete. Concrete is exceedingly troublesome material in which to drill deep holes, and this statement is particularly true if the concrete is green. The following mode of procedure proved successful in drilling 1/2 in. Anchor bolt holes 6 FT, and over in depth in green concrete. The apparatus used is shown by Fig. 303. redrawn from a rough sketch made on the work by one of the authors and only approximately to scale. The drill is hung on a small pile driver frame, occupying exactly the position the hammer would occupy in a pile driver, and is raised and lowered by a hand windlass. By this arrangement, a longer drill could be used than with the ordinary tripod mounting, and less changing of drills was necessary. A wide flare bit was used, permitting a small copper pipe to be carried into the hole with the drill. Through this pipe, water was forced under pressure, carrying off the chips so rapidly that no wedging was possible. By this device, drilling, which had previously cost over 25 CTS, a hole was done at a cost of less than 5 CTS. A hole. In removing an old cable railway track in St. Louis, Mo, holes 8 ins deep were drilled in the concrete with a No. 2 little Jap drill using a 1/8 quarter in, bit and air at 90 pounds, pressure. A dry hole was drilled, the exhaust air from the hollow drill blowing the dust from the hole, keeping it clean. The concrete was about 18 years old and very hard. 2 holes across track were drilled, 1 10 ins. Inside each rail. Lengthwise of the track, the holes were spaced 24 ins. Apart, or 4 pairs of holes between each pair of yokes. Common labor was used to run the drills, and very little mechanical trouble was experienced. 3 cars were fitted up, 1 for each car being equipped with a motor-driven air compressor, water for cooling the compressors being obtained from the fire plugs along the route. The air compressors were taken temporarily from those in use in the repair shops, no special machines being bought for the purpose. Electricity for operating the air compressor motors was taken from the trolley wire over the tracks. The car was moved along as the holes were drilled, air being conveyed from the car to the drills through a flexible hose. 2 drills were operated normally from each car. One of the air compressors was exceptionally large and at times operated 4 drills. The total number of holes drilled in the reconstruction of the track was 31,000. The total feet of hole drilled was 20,700 FT, with the best one of the plants operating 2 to 3 drills 38 in. Holes are 20. 3 FT of hole were drilled per hour per drill at a labor cost of 7 CTS per foot. For blasting, a 1 lb, charge of 40%. Dynamite was used in each hole. A fulminating cap was used to explode the charge, and 12 holes were shot at one time by an electric firing machine. The dynamite was furnished from the factory in 1 lb. Packages, and all the preparation necessary on the work was to insert the fulminating cap in the dynamite, tamp the charge into the hole, and connect the wires to the firing machine. In order to prevent any damage being done by flying rocks at the time of the explosion, each blasting gang was supplied with a cover car, which was merely a flat car with a heavy bottom and side boards. When a charge was to be fired, this car was run over the 12 holes and the side boards let down, so that the charge was entirely covered. This work was remarkably free from accidents. There were no personal accident claims whatever, and the total amount paid out for property damages for the whole 6 miles of construction was $685. Most of this was for glass broken by the shock of explosion. There was no glass broken by flying particles. The men doing this work, few of whom had ever done blasting before, soon became very skillful in handling the dynamite, and the work advanced rapidly. The report made by the firing of the 12 holes was no greater than that made by giant firecrackers. For the drilling and blasting, the old rail had been left in place to carry the air compressor car and the cover car. After the blasting, this rail was removed and the concrete, excavated to the required depth. In most cases, the cable yokes had been broken by the force of the blast. Where these yokes had not been broken, they were knocked out by blows from pieces of rail. The efficacy of the blasting depended largely upon the proper location of the hole, where the holes had been drilled close to the middle of the concrete block, so that the dynamite charge was exploded a little below the center of gravity of the section. The concrete was well shattered and could be picked out in large pieces. Where the hole had been located too close to either side of the concrete block, however, the charge would blow out at one side, and a large mass of solid concrete would be left intact on the other side. The total estimated quantity of concrete blasted was 6,558 ku. IDs, or 0.2 ku yd, of concrete per lineal foot of track. The cost of the dynamite delivered in 0.1 lb packages was 13 CTS per pound. The exploders cost $0.0255 each. The cost of drilling and blasting was as follows: item, per mile, per lin, FT per ku, YD. Labor, drilling, $1.89, 76 $0, 0.17 $0, 0.85 blasting labor and materials, 285, 12 0. 0.54 0, 268. Total drilling and blasting, $374, 88 $0, 0.71 $0, 353 fig, 304. Bench Monument, Chicago, Ill. The cost of blasting with labor and materials separately itemized was as follows per cubic yard. Dynamite and exploders $0. 192 labor 0.76, total $0. 268 2 cubic yards of concrete were blasted per pound of dynamite. Bench monuments, Chicago, Ill. The standard bench monuments, Fig. 304 used in Chicago, Ill, are mostly placed in the grass plot between the curb and the lot line so that the top of the iron cover comes just level with the street grade or flush with the surface of the cement walk. The monument consists of a pyramidal base 6 ft, high and 42 ins, square at the bottom with a quarter in, times 2 ft, copper rod embedded, and of a cast iron top and cover constructed as shown by the drawing. Mr. W. H. Hedges, Bench and Street Grade Engineer, Department of Public Works, Chicago, Ill, gives the following data regarding quantities and cost. The materials required for each monument are 1. 78 ku yd, crushed stone 0.6 ku yd, torpedo sand 1.5 bbls. Cement 60 ftb, lumber 1 times 24 in. Copper rod 1 top and cover. A gang consisting of 1 foreman, 4 laborers and 2 teams construct from 1 to 3 monuments per day, the average number being 2 per 8-hour day. In 1906, the average cost of the monuments was $24, 12 each based on above material and labor charges. Fig. 305. Base for wooden pole, Fig. 306. Mile post, Chicago and Eastern Illinois Rye, pole base. Figure 305 shows a concrete base for transmission line poles invented by Mr. M. H. Murray of Bakersfield, Cal., and used by the Power Transit and Light Co. of that city. These bases are molded and shipped to the work ready for placing. They weigh about 420 pounds each. One base requires 37.5 pounds of 2 times in. Steel bar 40 pounds, of Portland cement 3 ku, ft, of broken stone or gravel and enough sand to fill the form or mold, which is 10 times 10 ins, by 4.5 ft. Unskilled labor is employed in the molding, and 2 men can mold 10 bases per 8-hour day. The cost of molding is as follows per base. 2 men at $2 per day, $0. 40 brace irons per set, 2, 51 to 9 coup, YD. Stone at $4, 050, 45 40 pounds. Cement at 1/2 CTS, 0, 60 sand, 0, 15. Total cost $4. 10 2 men at $2 per day, each set 5 bases in 8 hours, making the cost of setting 80 CTS per base. The bases were sunk to a depth of 3 ft, 3 ins. In many cases, they were placed under poles without interrupting service by sawing off the pole, dropping it into the ground, placing the new base and setting the sawed-off pole on it and bolting up the straps. Mile post, Chicago and Easton, Illinois, RR. The dimensions of the post are shown by Fig. 306. Each post weighs 498 pounds. They are made when other concrete work is being done. The form is laid flat with the molds for the letters on the bottom and sides are plastered with mortar, which is backed up with a 1:1 to 2 stone concrete. The cost of the post is given as follows: a quarter barrel of cement at $2, $0, 5,267 pounds, crushed stone 0, 133 pounds, sand 0, 1 hours labor at 15 CTS, 21 hour carpenter changing letters at 25 CTS, 0.08 coloring cement 0.02 total $0. 82 bonding new concrete to old. Concrete which is set hard has a surface skin or glaze to which fresh concrete will not adhere strongly unless special effort is made to perfect the bond. Various ways of doing this are practiced. The most common is to clean the hardened surface from all loose material and give it a thorough wash of cement grout against which the fresh concrete is deposited and rammed before the grout has had time to set. Washing the old surface with a hose or scrubbing it with a brush and water improves the bond, as does also the hard tamping of the concrete immediately over the joint. Mortar may be used in place of grout. The thorough cleansing of the surface is, however, quite as essential as the bonding coat. In fact, in the opinion of the authors, it is more essential. As a rule, a good enough joint for ordinary purposes can be got by tamping the fresh concrete directly against the old concrete, without grout or mortar coating, if the surface of the latter is thoroughly cleaned by scrubbing and flushing. The secret of securing a good bond between fresh concrete and concrete that is set lies largely in getting rid of the glazed skin and the slime and dust which forms on it. Washing will go far toward doing this. The glazed skin can be removed entirely by acid solutions, but the acid wash must be flushed free from the surface before placing the fresh concrete. Ransomite, made by the Ransom Concrete Machinery Co., Dunellen, N.J., is a prepared acid wash which to the author's knowledge has given excellent success in a number of cases. The glaze coat can also be removed by picking the hardened surface, but the picking should be followed by washing to remove all loose chips and dust. Dimensions and capacities of mixers. In planning plant layouts, it is often desirable to know the sizes, capacities, etc., of various mixers in order to make preliminary estimates. Tables Roman 22 to Roman 33 give these data for a number of the more commonly employed machines. The Eureka, the Advanced, and the Schaeffler mixers are continuous mixers, and the others are batch mixers. Table Roman 22, sizes, capacities, and weights of advanced mixers. Cement Machinery Co., Jackson, Mitch. Height ground to hopper top 3.6, width over all 3.6, length over all on trucks 10.6, capacity per hour, coup. IDS. 25 to 75 horsepower, engine 2 weight, on trucks without power, pounds. 1,700 on trucks, steam engine 2,000 on trucks, gas engine 2,200 on trucks, steam engine and boiler 2,500 table Roman 23. Sizes, capacities and weights of Schaeffler proportioning mixers. The Hotwick Machinery Co., Jackson, Mich. Mixer number. No, 2, no, 2.5, no, 3. Dimensions of hopper ins. 55 times 33, 53 times 33, 60 times 40 height, from ground to top of hopper ins. 43, 43, 48, width overall on trucks ins. 46, 46, 46, length overall on trucks ins. 126, 126, 132 hourly capacity in cubic yards, 5 to 6, 8, 12 to 15 horsepower required. Gasoline engine 2, 3, 4 horsepower required, steam engine. 3, 4 weights, on trucks without power, pounds. 2,400, 2,900, 3,300 on trucks, gasoline engine, pounds. 3,000, 3,600, 4,500 on trucks, steam engine, pounds. 2,800, 3,330, 4,000 on trucks, steam engine and boiler, pounds. 3,500, 3,700, 4,800 table Roman 24. Sizes, capacities and weights of Eureka mixers. Eureka Machine Co., Lansing, Mich. Mixer number no. 81 no. 82 no. 83 no. 84 no. 25 no. 23 size hoppers ins. Sand 18 times 25 a half. 18 times 25 a half, 18 times 25 a half, 18 times 25 a half, cement 17 times 25 a half, do. 17 times 25 a half, 17 times 25 a half, 17 times 25 a half, stone 30 times 25. 30 times 25. Height, ground to hopper top 49. 49, 49, 49, 49, 49. Width overall on trucks 40, 40, 40, 40, 40, 40. Length overall on trucks 12 minus 9, 10 minus 0, 10 minus 0, 10 minus 0, 8 minus 0, 8 minus 0. Capacity per hour, Q. IDS. 10 to 1810 to 1810 to 1810 to 1810 to 182 to 4 engine horsepower 3 SDM 3 SDM 3.5 gas 3L motor pulley hand boiler horsepower 4 1980 1400 1400 weight on trucks no power 1980 1980 1980 weight trucks steam engine 2,800. Weight trucks gas engine 2,300. Weight trucks eng and boiler 3,000. Table Roman 25. Sizes, capacities and weights of Snell mixers. RZ. Snell MFG. Co. South Bend Ind. Mixer number. No. 0. No. 1. No. 2. No. 3. Size batch Q FT. 371124 capacity per hour Q IDS 2.5 5820 speed revs per min 30 25 19 weight on skids with pulley pounds 480 800 900 2000 with engine pounds 800 1550 2000 and 53,500 with eng and boiler pounds 2,170, 2,900, 4,000 weight on wheels. With engine, pounds. 1,100, 2,200, 3,004, 154,700. With engine and boiler, pounds. 3,570, 4,700, 55,200 engine. Size cylinder ins. 4 times 6 3 times 4.5 4 times 5 5 times 6.5 rated horsepower 1.5 4 5 6 boiler Size, ins, 24 times 60, 26 times 60, 30 times 60 rated horsepower, 568 outside dimensions on skids 29 times, 434 times 56. 4 times 6, 6 times 9 total height on skids 38, 46, 556, table Roman 26. Sizes, capacities, and horsepower of Ransom. Mixes, Ransom Concrete Machinery Co. Dunellen N.J. Mixer number, No. 1, No. 2, No. 3, No. 4. Size batch, Coup, FT. 10 to 14, 20, 30, 40 capacity per 8 SHA, Coup, IDS. 10, 20, 30, 40 speed, revs per min. 16, 15, 14, a half 14 weight on skids, pulley or gear pounds. 3,300, 3,600, 55,900, 7,400 with engine, pounds. 4,600, 5,000, and 57,700, 9,250 with engine and boiler, pounds. 6,450, 8,700, 12,200, 14,700 weight on wheels, with engine, pounds. 5,100, 5,500, 58,200, 9,750 with engine and boiler, pounds. 6,950, 9,200, 12,700, 15,000 engines. Size cylinder, ins. 6 times 6, 7 times 7, 8 times 8, 9 times 9, rated horsepower, 7, 10, 14, 20 boiler. Size, ins. 36 times 69, 42 times 75, 42 times 87, 48 times 93, rated horsepower, 10, 15, 20, 30, table Roman 27. Sizes, capacities, and horsepowers of Chicago improved cube mixers. Municipal Engineering and Contracting Co. Chicago, Ill. Mixer number, No. Handy, No. 6, No. 11, No. 17, No. 22, No. 33, No. 64. Size batch, Coup. FT, 2, a half, 6, 11, 17, 22, 33, 64 capacity per 8 SHA. Coup. IDS. 5, a half, 13, 24, 40, 50, 70, 120 speed, revs, per min. 24, 20, 18, 17, 16, 15, 12 weight on skids, pulley or gear, pounds. 1,000, 1,900, 2,800, 5,000, 7,000, 9,600, 19,000 with engine, pounds. 2,500, 3,600, 6,100, 8,200, 12,000 with eng. And boiler, pounds. 3,100, 4,300, 7,800, 10,000, 16,000 weight on wheels. With engine, pounds. 1,400, 3,200, 4,500, 7,100, 9,500, 15,000 with eng. And boiler, pounds. 4,000, 6,000, 8,800, 10,000, 300, 17,000 engine. Size cylinder, ins. 4 times 4, 6 times 6, 6 a times 7, 7 times 8, 8 times 9. Rated horsepower 2, 3, 6, 8, 12, 15, 30 boiler. Rated horsepower 4, 8, 10, 15, 18, 35 width overall 4 minus 5, 5 minus 10, 7 minus 1, 7 minus 8, 8 minus 6, 9 minus 8. Length overall 4 minus 10, 6 minus 9, 8 minus 0, 8 minus 10, 10 minus 2, 13 minus 6 height bought. Sill to charging hopper 3 minus 4 a quarter, 3 minus 5, 3 minus 10, 4 minus 7, 5 minus 0, 5 minus 9. Additional height on wheels 9, 1 minus 5, 1 minus 5, 6, 5 a half table Roman 28. Sizes, capacities, and horsepowers of crop mixers. AJ Crop Concrete Machinery, Chicago, Ill. Mixer number, No, 0, no, 1, no, 2, no, 3, no, 4, size, batch, coup, FT, 7 to 8, 10, 13, 16, 20, cap, per HR, coup, IDS, 15, 20, 25, 30, 40, speed, revs, per min, 12, 10, 10, 10, 10, weight on skids, with engine, pounds, 1,375, 1,650, 1,719, 175, 2,100, with eng, and boiler, pounds, 2,575, 2,950, 3,000, 3,775, 3,900, weight on wheels, with engine, pounds, 1,775, 2,000, and 50, 2,200, 2,475, 2,600, with eng, and boiler, pounds, 2,900, 3,350, 3,400, 4,250, 4,350, engine. Size cylinder, ins. 4 times 4, 5 times 5, 5 times 5, 6 times 6, 6 times 6. Rated horsepower 35577 boiler. Size inside 24 times 4, 24 times 6, 24 times 6, 30 times 6, 30 times 6, rated horsepower 46699 out. Dimensions on skids 40, 40, 40, 48, 48. Total height 50, 56, 56, 56, 62 height FR. Ground on trucks, charging ins. 2020, 2020, 20 discharging ins. 30, 30, 30, 30, 30 table Roman 29 sizes, capacities, and horsepowers of Chicago concrete mixers. Chicago Concrete Machinery Co., Chicago Ill. Number of mixer, no, 0, 0, no, 0, no, 1, no, 2. Standard charge in coup. FT. Cement 1/2, 1, 1, 2. Sand 1/2, 2/2, 4, 8. Stone 358, 16 total unmixed batch in coup. FT 58 1/2, 13, 26 mixed concrete per batch, loose in coup. FT 3 1/2, 6, 9, 18 cubic yards of unmixed material per hour, 45 batches per hour, 8, 14, 21, 42 cubic yards of mixed concrete per hour, 45 batches per hour, 6, 10, 15, 30 minimum horsepower. Required 2, 4, 6, 8 revolutions of driving pulley per min, 200, 190, 185. 170 revolutions of drum per min, 2018, 1513 diameter, and face of driving pulley 20 times 3, 1/2 20 times, 4 1/2 24 times 5, 1/2 28 times 6, 1/2 weight. On skids with pulley, pounds, 1,550, 2,150, 2,900, 4,850. On truck with pulley or gears, pounds, 1,800, 2,550, 3,500, 5,150 on skids with scent. Engine only, pounds, 2,400, 3,400, 4,600 on truck with scent. Engine only, 2,900, 4,000, 5,300 on skids with scent. Eng. And boiler, pounds, 2,800, 4,700, 6,000 on truck with scent. Eng, and boiler, pounds, 2,400, 4,200, 5,750, 7,850 on skids with gasoline engine, pounds, 2,000, 3,500, 5,000, 6,500 on truck with gasoline engine, pounds. 2,400, 4,300, 5,800, 7,800 table XXX, sizes, capacities, and horsepowers of co-ring mixers. Co-ring machine Co., Milwaukee Wise, mixer number, no, 0B, no, 1B, no, 2B, no, 3B, capacity per charge in Ku. FT 71122 27 capacity per hour in Ku. IDS 714 25 30 horsepower. Steam engine 46810 horsepower. Steam boiler 5810 14 horsepower. Gasoline engine 4610 12 horsepower. Electric motor 567. A half 10 speed of drum 2017. 15 speed of intermediate shaft 132. 108 75. Weight of mixer on skids 1,800 2,800 5,200 5,500. Weight of mixer on skids with steam ang 2,300 3,556,500 7,000. Weight of mixer on skids with steam engine and boiler 3,300 5,000 8,000 9,300. Weight of mixer on skids. Gasoline engine and housing 3,000 4,400 7,500 8,600. Weight of trucks with pole 400 600 850 950. Weight of automatic loading bucket complete 500 700 1,000 1,100. Weight of mixing through complete 200 250 400 400. Table Roman 31. Sizes, capacities, and horsepowers of Smith mixers. Contractors Supply and Equipment Co., Chicago, Ill. Mixer number: No 0, No 1, No 2, No 2.5, No 4, No 5. Stand Charge Ku, FT. Cement 1 1 2 2 3 4. Sand 2.5 4 6 7.5 10.5 14. Stone 5 8 12 15 21 28. Total unmixed per batch Ku, FT. 8.5 13 20 24.5 34.5 46. Mixed material per batch loose Ku, FT. 6 9 13.5 16.5 22 30 cubic yards mixed per hour. Up to 9 20 30 39 46 62. Power required. H. P. 4 6 8 10 15 19 revs. Per minute of driving pulley 218 180 173 162 160 125 diameter and face of driving pulley ins 20 times 4.5 24 times 5.5 28 times 5.5 28 times 6.5 36 times 6.5 48 times 7.5. Weight on skids with pulley only pounds. 1,740 2,500 3,600 4,400 6,200 7,900. Weight on truck with pulley or gears pounds. 2,200 3,650 4,750 5,500 7,400. Weight on truck with steam ang and boil pounds. 3,750 5,600 7,200 8,600 11,400. Weight on truck with gasoline engine pounds. 4,000 5,100 7,400 9,300. Table Roman 32. Sizes, weights, and capacities of polygon mixer. Waterloo Cement Machinery Co., Waterloo, Iowa. Mixer number: No 4, No 5, No 6, No 7. Maximum charge Ku, FT. 6 10 12 16 cubic yards mixed per day 10 HRS. Up to 60 191 130 180. Weight on skids with pulley approx. 1,600 2,200 3,500 4,000. Weight on skids with steam engine and boiler approx. 3,100 3,900 5,500 6,200. Weight on skids with gasoline engine approx. 2,900 3,900 5,100 5,700. Weight on trucks with steam engine and boiler, approx. 3,600, 4,600, 6,000, 7,000. Weight on trucks with gasoline engine, approx. 3,400, 4,650, 5,700, 6,750. Data for estimating the weight of steel in reinforced concrete. Architects and engineers' plans record the steel used in reinforced concrete in various ways. Sometimes complete schedules of shapes, dimensions, and weights of the various reinforcing elements are drawn up and submitted to bidders with the plans. In such cases, the estimating is usually a simple problem for the contractor. In other cases, the amount of steel that will be required is stated as a percentage of the volume of the concrete. In still other cases, the detailed drawings merely show the number, location, and dimensions of the reinforcing bars, stirrups, etc., and the contractor has to compile from them his own schedule of quantities. The following tables and discussion will aid the contractor in making his estimates. Before proceeding with these data, however, the authors would strongly advise that to facilitate rapid estimating, the contractor should keep accurate records of all reinforced concrete structures in such form as to show the percentages of steel used. In doing this, however, he should be careful to separate the foundations, etc., which are not reinforced from the superstructure which is reinforced. A reinforced concrete arch bridge, for example, usually rests on piers and abutments which are not reinforced. Do not lump together all the concrete in recording the weight of reinforcement used, but separate the reinforced arch from the unreinforced portions. Method of computing weight from percentage of volume. In a cubic yard of concrete, there is 1% of 27 cu ft, or 0.27 cu ft of steel if the reinforcement is 1%. Now a cubic foot of steel weighs 490 pounds, but for all practical purposes we can call it 500 pounds. Hence reinforced concrete containing 1% of steel has 0. 27 times 500 equals 135 pounds per cubic yard. Table Roman 33 has been computed in this manner. Knowing the price of steel, it is a matter of simple multiplication to estimate from the table the cost of steel for any percentage of reinforcement, weights and dimensions of plain and special reinforcing metals. Steel for reinforcement is used in the shape of plain round and square bars, deformed bars, woven and welded netting, and metal mesh of various sorts. Tables Roman 34 to Roman 37 show the weights, dimensions, etc. of these various metals. Table Roman 33, showing weight of steel per cubic foot and per cubic yard of concrete for various percentages of reinforcement. Percent of steel. Pounds, steel per cu, ft. Pounds, steel per cu, yd. 0, 21, 0, 0, 27, 0, 0, 25, 1, 25, 33. 80, 31, 50, 40, 50, 35, 1, 75, 47, 30, 42, 00, 54, 00, 45, 2, 25, 60, 80, 52, 50, 67, 50, 55, 2, 75, 74, 30, 63, 00, 81, 00, 65, 3. 2587, 50, 73, 50, 94, 50, 75, 3, 75, 101, 30, 84, 00, 108, 00, 85, 4, 25, 114, 80, 94, 50, 121, 50, 95, 4, 75, 128, 31, 005, 00 135, 0 Table Roman 34 weights of round and square bars of dimensions commonly used for reinforcing concrete. Thickness or diameter in inches, weight of square bars, pounds per ft, weight of round rods, pounds per ft. 1/16 0, 013 0, 010 0, 053 0, 042 3/16 0, 119 0, 094 1/4 0, 212 0, 167 5/16 0, 333 0, 261 0, 478 0, 376 7/16 0, 651 0, 511 1/2 0, 850 0, 668 9/16 1, 076 0, 845 1, 328 1, 043 11/16 1, 607 1, 262 3/4 1, 913 1, 502 2, 608 2, 044 13, 402, 671 4, 303 3, 381 1/4 5, 312 4, 172 1 1/2 7, 656, 008 1 3/4 10, 404 4, 178 2 13, 610, 68 Table Roman 35 dimensions and weight of expanded metal. Mesh, inches, sectional area SQ, ins per ft, width, weight pounds per SQ ft, standard 1/2 0, 209 0, 74 standard 3/4 0, 225 0, 80 standard 1 1/2 0, 207 0, 70 standard 2 0, 166 0, 56 standard 3 0, 0 83 0, 28 light 3 0, 148 0, 50 standard 3 0, 178 0, 60 heavy 3 0, 267 0, 90 extra heavy 3 0, 356 1, 20 standard 3 0, 401, 38 standard 3 0, 602, 07 old style 4 0, 093 0, 42 standard 6 0, 245 0, 84 heavy 6 0, 368 1, 26 Table Roman 36 dimensions and weight of con rib metal, size no, section area per ft, width SQ, ins, weight per SQ ft, pounds 20, 54 2, 13 30, 36 1, 43 40, 27 1, 0850, 22 0, 87 60, 18 0, 72 70, 15 0, 62 80, 14 0, 55 Table Roman 37 weights of deformed bars of dimensions commonly used for reinforced concrete. Size ins, weight pounds per ft, area SQ, ins, size ins, weight pounds per ft, area SQ, ins, ransom twisted bar, new style corrugated bar. 1/4 0, 212 0, 063 1/4 0, 24 0, 06 1/2 0, 85 0, 25 1/2 0, 85 0, 25 1, 32 0, 319 1, 33 0, 39 3/4 1, 91 0, 563 3/4 1, 91 0, 56 2, 6 0, 765 2, 60 0, 77 13, 41, 0 0 0 13, 41, 001 1/4 5, 31, 563 1 1/4 5, 31, 56 diamond bar, universal corrugated bar, a half 0, 85 0, 25 a times 1 0, 73 0, 19 1, 33 0, 39 5 slash 16 times 1 a quarter 1, 18 0, 32 3 quarters 1, 91 0, 56 times 1 1, 35 0, 41 2, 60 0, 76 times 1 3 quarters 1, 97 0, 54 1 3, 41 0 0 times 2 2, 27 0, 65 1 a quarter 5, 31 1, 56 times 2 a half 2, 85 0, 80 no, 1 mil Thatcher bulb bar, no, 2 mil. A quarter 0, 16 0, 0 47, a half 0, 61 0, 18 a half 0, 58 0, 17 0, 95 0, 28 0, 92 0, 27 3 quarters 1, 39 0, 41 3 quarters 1, 34 0, 39 1, 87 0, 55 1, 79 0, 53 1 2, 42 0, 71 1 2, 32 0, 68 1 a quarter 3, 74 1, 10 1 a quarter 3, 55 1, 0 4 1 a half 5, 31, 56 1 a half 5, 21, 53 1 3 quarters 7, 0 7 2, 0 8, 2 9, 0 2 2, 65, monolith bar, twisted lug bar, 0. 4 0, 55 0, 25 a quarter 0, 222 0, 625 a half 0, 85 0, 32 a half 0, 87 0, 250, 1 35 0, 3906, 3 quarters 1, 94 0, 56 25 0, 8 2, 18 0, 64 2, 64 0, 76 56 13, 37 1, 0 0 13, 45 1, 0 0, 1 a quarter 5, 37 1, 56 25 1 a half 7, 75 2, 25 1 a half 7, 72, 25 cup bar 0, 48, a half 0, 86. 1, 35, 3 quarters 1, 95, 2, 65, 1, 3, 46, 1, 4, 38, 1 a quarter 4, 51 recipes for coloring mortars. The following recipes for coloring cement mortar have been found reliable, the weights given being weight of coloring matter per bag of cement, and for a 1 to 2 mortar. Brown stone, 4 to 5 pounds, brown ochre or a half lb. Best quality roasted iron oxide, buff stone 4 pounds, yellow ochre, red stone 5 pounds, raw violet iron oxide, bright red stone 5½ to 7 pounds, English or Pompeian red, blue stone 2 pounds, ultramarine blue, dark blue stone 4 pounds, ultramarine blue, slate lamp black ½ lb, light slate 4 pounds, dark blue slate, light terracotta 2 pounds, Chattanooga iron ore. Chapter 55. Resistance to penetration by water is desirable in all concrete structures, and is essential in such structures as tanks, reservoirs, vaults, subways, basements, and roofs. Concrete, as it is ordinarily made, is pervious to water. Hence, to secure concrete structures through which water will not penetrate, some method of waterproofing the concrete must be employed. Many methods have been proposed and are being used. None of these methods is without faults. The best one of them has not yet been determined, and the evidence available as to their comparative merits is biased and conflicting. For these reasons, any discussion of waterproofing for concrete is at the present time bound to be unsatisfactory. Methods of waterproofing may be roughly classified as follows. 1. Use of mixtures so proportioned as to be impervious. 2. Admixture of substances designed to produce impermeability. 3. Use of waterproof coatings, washes, or diaphragms. In succeeding sections, enough examples of each method are given to indicate current practice. No attempt has been made to catalog all the waterproofing substances and systems being promoted. There are too many of them. The art of waterproofing concrete is in a transition stage. Outside of the manufacturers of waterproofing material, the art has received serious study by comparatively few persons. No comparative tests by independent investigators are available. Practical experience with most of the materials used has not extended over a long enough period of time to permit true conclusions to be drawn. Students of the subject are not even agreed upon the broad questions whether it is better to work toward developing an impervious concrete or toward perfecting a waterproof covering for concrete. On the minor subdivisions, there is no agreement at all. In the present state of the art, one can lay fast hold to only 3 things. The first is that waterproofing is one component of a system of drainage. The second is that structures must, to get the best results, be designed with the fact in mind that waterproofing is a component structural element. And the third is that skilled and conscientious workmanship are essential elements in the success of all waterproofing materials and methods. Impervious concrete mixtures. The compounding of the regular concrete materials so as to produce an impervious concrete has been made the subject of numerous experiments. The most elaborate of these experiments were those conducted over a period of 5 years by Mr. Ferret, of the Boulogne, France laboratory of the Ponts et Chaussées. Ferret's experiments led him to the following conclusions: that in all mortars of granulometric composition, the most permeable are those which contain the least quantity of cement. Of all mortars of the same richness, but of varying granulometric composition, those which contain very few fine grains are much more permeable. They are the more so where, with equal proportions of the fine grains, the coarse grains predominate more in relation to the grains of medium size. The minimum permeability is found in mortars where the proportion of medium-sized grains is small, and the coarse and fine grains are about equal to each other. Mr. Ferret also found that permeability decreased with time, and that wet mixtures were less permeable than dry mixtures. Tests made by Messrs. J. B. McIntyre and A. L. True at the Thayer School of Civil Engineering in 1902 gave the following results. All the specimens composed of 1-to-1 mortar in the proportions of 30, 35, 40, and 45% of the whole mass were impermeable. Some of the specimens composed of 1-to-2 mortar in the proportions of 40 and 45% were also impermeable, as well as the 1-to-2-to-4 and 1-to-2-to-4 mixtures. All other mixtures leaked at the high pressure 80 pounds per SQ and in a general way exhibited a degree of imperviousness in direct proportion to the proportion of mortar in them, with the lower pressures from 20 pounds per SQ up, as well as for the ATLB pressure. Other tests confirm those cited. In general, we may conclude that those mixtures richest in cement and mortar are the most impervious. It is doubtless practicable by exercising proper care to proportion, mix and place a concrete mixture, which will be so nearly impervious that visible leakage will be small. The task, however, is one difficult to perform in actual construction work, and its accomplishment is never certain. Star-Stettin cement. Star-Stettin cement is a Portland cement made by grinding a clinker which has been impregnated with substances which impart waterproofing properties to the ground product. The process is the invention of Richard Liebold, and the cement is made by the Stettin Portland Cement Works, Stettin, Germany. It is asserted that a 1:4 fine sand mortar made with this cement is impervious. To use it, the ordinary precautions adopted in the employment of Portland cement are necessary, and in addition the following. The cement must be mixed with moist instead of dry sand before the water is added. The sand should be clean, sharp, and fine of grain. The mortar must be more perfectly mixed than ordinarily, and somewhat more water should be used than is ordinarily used. Perfectly even mixing is essential to the best results. Medusa waterproofing compound. This compound is a dry powder which is mixed with the cement in proportions of from 1% to 2% by weight, or from 4 pounds to 8 pounds per barrel of cement. The compound costs 12 CTS per lb, so that its addition increases the cost from 48 to 96 CTS per barrel of cement. Thorough mixing of the compound with the cement is of the utmost importance. Otherwise, none but the ordinary precautions in the use of Portland cement is necessary. Absorption tests on concrete blocks treated and untreated with the compound, and 9 months old, have shown the absorption of treated blocks to be about 1/4 or 1/5 that of untreated blocks. The compound is made by the Sandusky Portland Cement Co., Sandusky, Ohio, Novoid waterproofing compound. This compound is a dry powder which is mixed dry with the cement in the proportion of 1 to 2%, by weight, or about 1 to 2 pounds per bag of cement. The compound costs 12 CTS per pound, or about from 48 to 96 CTS per barrel of cement. Directions for making waterproofing mortar are: to 100 pounds of Portland cement add 2 to 2.5 pounds of compound and 200 pounds of clean and sharp sand, and mix the materials dry and very thoroughly. The water is then added in the proportion necessary to make a good working mortar, and the mortar mixed and applied in the ordinary manner. Used as a wash, 2 pounds of compound are thoroughly mixed dry with a bag of cement. Any portion of the mixture is then mixed with water to produce a creamy grout, which is applied to a thoroughly wet surface with a brush. This compound is made by the Abbey Dodge Brooks Concrete Co., Newark, N.J., impermeable coatings and washes. The most common means employed for rendering concrete structures waterproof is to coat or wash the surface with some substance itself impervious to water, or having the property of closing the pores of the surface skin of concrete, so that water cannot penetrate. Bituminous coatings. Bituminous coatings of one composition or another are among the most commonly used of impermeable coatings. The bituminous compound is used both alone and in combination with layers of a fabric of some sort to form the coating. Where bituminous coatings are used on surfaces exposed to the sun and frost, attention must be given to the fact that a compound of different properties is required where the range of temperature is great than is required where this range is smaller. Asphalt, for example, should have a flow point of 212 degrees F and a brittle point of -15 degrees F when exposed directly to sun and frost, as compared with, say, a flow point of 185 degrees F and a brittle point of 0 degrees F when covered from the direct action of sun and frost. Another point to be kept in mind, particularly in using exterior coatings, is that the concrete surface must be properly prepared to receive the coating, or else it will peel off. The following are examples from actual practice of waterproofing with bituminous coatings. The following method of waterproofing with asphalt coating is given by W. H. Finley, The asphalt used must be of the best grade, free from coal tar or any of its products, and must not volatilize more than 0.5% under a temperature of 100 degrees F. For 10 hours, it must not be affected by a 20%. Solution of ammonia, a 35%. Solution of hydrochloric acid, a 25%. Solution of sulfuric acid, or a saturated solution of sodium chloride. For structures underground, a flow point of 185 degrees F and a brittle point of 0 degrees F shall be required. If the surface cannot be made dry and warm, it should first be coated with an asphalt paint made of asphalt reduced with naphtha. The asphalt should be heated in a kettle to a temperature not exceeding 450 degrees F. It has been cooked enough when a piece of wood can be inserted and withdrawn without the asphalt clinging to it. The first coat should consist of a thin layer poured from buckets on the prepared surface and thoroughly mopped over. The second coat should consist of a mixture of clean sand and screenings, free from earthy admixtures, previously heated and dried, and asphalt, in the proportion of 1 of asphalt to 3 or 4 of sand or screenings by volume. This is to be thoroughly mixed in the kettle and then spread out on the surface with warm smoothing irons, such as are used in laying asphalt streets. The finishing coat should consist of pure hot asphalt spread thinly and evenly over the entire surface, and then sprinkled with washed roofing gravel, torpedo sand, or stone screenings to harden the top. The thickness of the coating will depend on the character of the work and may vary from 3/4 in to 2 ins in thickness. Several firms manufacture and sell ready-made priming paints and mastics for waterproofing concrete by substantially the above method. Saco compounds made by the Standard Asphalt and Rubber Co. of Chicago, Ill. are examples. Saco waterproofing is a compound analyzing 99.7% pure bitumen and having a range of ductility of 200 degrees F. In waterproofing large car barn roofs of concrete in Chicago, the concrete was first swept clean, and a coat of priming compound was thoroughly brushed in. On the priming coat was mopped a coat of waterproofing compound, applied hot, and covered with a layer of fine sand. The thickness of the completed coating was 1/16 in. Where a heavier waterproofing is necessary, the waterproofing compound is covered with 1 or more in coats of Saco mastic. The following bituminous coatings have been used in waterproofing concrete fortifications by the U.S. Army Engineers. Mobile, ALA. The top of the concrete was covered with a thin coat of 1 to 2 cement mortar and given a rough trowel finish. As soon as the surface was dry, it was covered with a layer of asphalt mastic 1 in, thick and rubbed down to a finish with dry sand and cement in equal parts. To prepare the mastic, take 500 pounds of Diamond T asphalt mastic, broken into small pieces, 30 pounds of Diamond T asphalt flux, and 5 pounds of petroleum residuum oil. When thoroughly melted, add 400 pounds clean, dry torpedo gravel previously heated. Stir gravel and asphalt until thoroughly mixed at a temperature of about 375 degrees F. Key West flour. The top of the concrete was covered with smooth plaster, proper slope for drainage being given. Above this, 2 layers of asphalt of an aggregate thickness of 3/4 in were applied. The composition of the asphalt was as follows: 440 pounds rock asphalt mastic, 3 gallons coal tar, and 5 gallons silicious sand. Delaware River defenses. The concrete was waterproofed with coal tar and sand. The tar was made hot and applied to the surfaces with rubber squeegees and then sanded. Joints were filled with the hot tar. A surplus of sand was left on for a few days and then swept off. 1 barrel of coal tar covered 2,279 SQ, FT, with 1 coat and cost $4, 25 per barrel delivered. The cost including material and labor was 0, 74 CT per SQ, FT. San Francisco Harbor. The roof had a pitch of about 3 and 20 and was covered with an earth fill. The concrete was troweled to a fairly smooth surface, was mopped with a heavy coat of roofing asphaltum or mastic, then covered with the heaviest grade roofing felt laid 3-ply, starting at the coping of the parade wall and made 4-ply in the gutter. On this assumed watertight surface 3-in. Book tile was laid with joints normal to the gutter and cemented. The purpose of the tile was to afford a free passage for the water as soon as it met the roof. The expectations were fully realized and no water or even a sign of moisture has appeared in this battery or at another of the same type since built after a fair test of time. The total cost of the work, including mastic, felt, and tile, was 17 CTS per SQ FT for 6,200 SQ FT, covering 3 roofs. In conclusion, it may be noted that any of the methods of constructing impermeable diaphragms can be used for constructing impermeable coatings. Cherelmy Stone Liquid Wash. This wash has been used in England for waterproofing and preserving masonry for some 20 years. It is a thin liquid compound which is applied to the surface with a brush. The stone or concrete surface is required to be dry and thoroughly clean, with all scale and loose particles removed. The standard treatment is 3 coats. 1 gallon of liquid is in most cases sufficient for treating. 3 coats, 25 SQ. IDS, but in exceptionally bad cases 1 gallon for 15 SQ. IDS has been found necessary. The precautions necessary for the successful use of the liquid are: it must be well stirred, it must be applied to a perfectly dry, clean surface, and it must be well rubbed into the masonry. The American agency for the liquid is Cherelmy & Co., Washington, D.C. Sylvester Wash. Waterproofing with Sylvester Wash consists in applying alternately to the concrete surface a soap solution wash and an alum solution wash. The soap solution is applied first, and it must be applied hot and to a dry surface. The alum solution is applied second and 24 hours after the soap solution and is applied cold. This constitutes one treatment. After 24 hours, a second treatment may be given, and as many treatments may be given as necessary. In some cases, as many as 6 treatments have been employed. The proportions of the solutions used in practice vary. In waterproofing the standpipe described in Chapter Roman 22, the soap solution consisted of 12 Oz. Pure castile olive oil soap per gallon of water, and the alum solution consisted of 2 Oz. of alum per gallon of water. In repairing the bottom of a reservoir lined with 4 to 6 ins of concrete, the following solutions were used: 3/4 lb. Olean soap to 1 gallon of water and 1/2 lb. Alum to 4 gallons of water. Both alum and soap were well dissolved and the soap solution was boiled. The boiling hot soap solution was applied on the clean, dry concrete. 24 hours later, the alum wash was applied cold. This treatment was repeated after 24 hours. 2 men applied the solutions, using whitewash brushes, while a third man carried pails of the solution. In making the soap solution, 2 men attended 4 kettles. 1 man kept up fires. 2 men carried solution to men applying it. The alum solution required fewer men, being made cold in barrels. After applying the second soap wash to the concrete slopes, the men had to be held by ropes to keep from slipping. The rope was placed around 2 men who started work at the top of the slope. a third man paying out the rope. The work was done in 8.5 days and cost as follows. Labor, 1,140 hours labor at 15 CTS, $171. 0083 hours foreman at 30 CTS, 24. 9083 hours waterboy at 6 CTS. 4. 98 ad for superintendents 15% 30. 13. Total labor $231. 01 materials 900 pounds. Olean soap at 4 1/3 CTS. $39. 210 pounds. Alum at 3 CTS. 6 3610 in. Whitewash brushes at $2. 2513. 56 stable brushes at $1. 25.7. 50. Total materials $66. 30 total labor and materials $297. 31 This covered 131,634 SQ. FT. Hence the cost of the 2 coats of soap and alum was $2. 26 per 1,000 SQ. FT, or 0.23 CT per SQ FT. The ordinary Sylvester wash as described above has been modified with success on government fortification work as follows. To 2 gallons of water add 1 lb, concentrated lye and 5 pounds. Alum and mix until completely dissolved. This is a concentrated stock solution. In use 1 pt of solution and 10 pounds of cement are mixed with enough water to make a mixture that will lather freely under the brush. 2 coats of this wash are applied, the second at any time after the first is dry, and the first as soon as the foams are removed from the concrete. The wash should be applied to a wet surface. If the concrete is dry, it should be wet down with a brush ahead of the wash. Sylvester mortars. In this class of coatings, the alum and soap are added to the mortar which is used for facing. A successful recipe for such a mortar is given as follows. To 1 part cement and 2 parts sand add 3/4 lb of pulverized alum for each cubic foot of sand and mix these ingredients dry. Then add the proper quantity of water, in which has been dissolved 3/4 lb of soap to the gallon, and mix the mortar thoroughly. Such a mortar is but slightly inferior in strength to ordinary mortar of the same proportions. In plastering, a clear water well to prevent leaking a 1 to 2 mortar was made as follows. 1/4 pounds of soap were dissolved in 15 gallons of water and 3 pounds of powdered alum were mixed with 1 bag of cement. 2 coats of plaster of an aggregate thickness of 1/2 in were applied and completely stopped the leaking. The cost of this treatment was as follows. 2 pounds. Soap with 24 gallons, water at 7.5 CTS. $0. 15-12 pounds. Alum at 3.5 CTS. 0.42. Total per barrel of cement $0. 57 in lining a new reservoir near Wilmerding, Pa. A mortar was made as follows. A stock solution of 2 pounds, caustic potash and 5 pounds. Alum to 10 quarts of water was made in barrel lots from which 3 quarts were taken for each batch of 2 bags of cement and 4 bags of sand. A batch of mortar covered an area 6 times 8 ft. With a 1 in coat. The extra cost of the waterproofing was 100 pounds. Caustic potash at 10 CTS. $10. 0070 pounds. Caustic potash at 9 CTS. 6. 3,960 pounds. Alum at 3.5, 3/3 and 4 CTS. 34. 3860 hours mixing at 15 CTS. 900 freight, express and haulage 11. 50. Total for 74,800 SQ. FT. $71. 18 This gives a cost of 95 CTS. per 1,000 SQ, FT, or less than 0.1 CT per SQ, FT. It was found that if less than 2 parts of sand to 1 part of cement was used, the mortar cracked badly in setting. Clean sand was imperative, as any organic impurities soon decomposed, leaving soft spots. Do not use an excess of potash. A slight excess of alum, however, does not decrease the strength of the mortar. Hydrolytic coating. This waterproofing is a dry mortar composed by mixing a cementing compound with sand and sold dry in sacks containing 96 pounds each. The dry mortar is mixed with water to proper consistency for plastering and is applied as a plaster to the surfaces to be waterproofed. The dry mortar is mixed with water to a grout of the consistency of thick cream, and then this grout is stiffened to the proper consistency by adding more dry mortar. Thoroughness of mixing is absolutely essential. The concrete surface is prepared by picking and scoring sufficiently to get a fresh surface and washing away all chips, dust, and loose material, or instead of picking in new work, the outer skin may be removed by a 1:9 muriatic acid solution, and then washed free of all acid and scrubbed with wire brushes. After preparing the fresh surface, it is well wetted, in fact water-soaked, so that, while not oozing moisture, it will absorb no more water. The mixed mortar is then applied with a trowel in a workmanlike manner. In mixing, no more than 8 gallons of water per barrel of mortar should be used. The coatings used are to in, for walls, and 1/2 to 3/4 in, for floors. The following estimate of cost is made by the manufacturers, the E.J. Winslow Co., Chicago, Ill. The figures are presented with the understanding that they are to be considered merely as average costs for waterproofing, without special construction, and subject to change in accordance with local conditions, and to the time of year when the work will need to be performed. Per SQ, FT. To prepare surfaces to receive coating may cost the contractor 5.5 CTS. The coating material FOB, Chicago, may cost the contractor 4.5 CTS. The labor of application may cost the contractor 7.5 CTS. Administration and incidental expenses may cost the contractor 7.5 CTS. 25 CTS. The lowest price yet asked for work was 20 CTS, and the highest 55 CTS. These two prices representing the opposite extremes of conditions that different jobs will present. Cement mortar coatings. Rich cement mortar mixtures offer considerable resistance to penetration by water, and when well made may be used with a fair degree of success to waterproof ordinary concrete. European engineers make wide use of mortar coatings for waterproofing tanks and reservoirs, and appear to have good success with them. The experience in this country is that no great reliance can be placed on them, where the pressures are at all large. Records of work done show both successes and failures, with no apparent reason for either so far as composition of mortar or quality of workmanship goes. A rich mortar plaster will reduce leakage and may prevent it entirely, but it is uncertain how far it will prove watertight. Oil and paraffin washes. The theory of the use of oil and paraffin washes is that the material soaks into the concrete and closes the surface pores against the penetration of water. Paraffin has been quite widely used for preserving stone masonry walls for buildings. It is applied hot, and in the best practice is applied to a dry, heated surface. Concerns doing such work on buildings have portable devices for heating the masonry. Oil is sometimes applied hot, but is more often flushed onto the surface and allowed to soak in as it will. Impermeable diaphragms. The most generally employed method of waterproofing concrete structures with the possible exception of painting and coating methods, is to embed in the wall, roof, and floor slabs a diaphragm that is impervious to water. Such diaphragms are usually composed of layers of waterproof felt or paper cemented together, and to the concrete by asphalt, coal tar pitch, or patented cementing compound. Another construction consists of a layer of asphaltic compound between two layers of cement mortar. In some cases, also the combination felt and cementing compound diaphragm is further strengthened by placing it between layers of mortar. In wall work, the diaphragm is frequently applied to the face of a single-layer brick wall, and the concrete filled against it. The brick wall may be further waterproofed by laying the brick in hot asphalt instead of in mortar. Within the last few years, a number of firms have devoted their efforts to producing special fabrics, felts or papers, and special cementing compounds designed to be used with the fabrics for waterproofing concrete. These fabrics and cements are in most cases superior in toughness, flexibility, ease of application, etc., to the ordinary roofing and waterproofing fabrics designed originally for general building purposes. Long Island subway. In constructing the Long Island subway, the roof was waterproofed according to specifications as follows. After the roof concrete was crowned, brought to a smooth surface, and thoroughly dried, it was swabbed over with hot melted, medium-hard, coal tar pitch to an even thickness of not less than 1 to 16 in. Immediately upon the first coat of pitch, and while it was still melted, was laid a covering of single-ply roofing felt, with the sheets lapping 4 ins on all cross joints and 12 ins on longitudinal joints. This felt was in turn mopped with pitch, and upon that again was laid another layer of roofing felt, which was given a final coating of pitch. The pitch used was of a grade somewhat softer than that used for roofing purposes, or such as would soften at a temperature of 60 degrees F, and melt at a temperature of 100 degrees F. The felt used consisted of pure wood paper pulp or asbestos pulp, which had been thoroughly treated and soaked in refined coal tar, and which weighed for single ply at least 15 pounds. Per 100 SQ, FT. After the waterproofing with pitch and felt had thoroughly hardened, it was plastered over with a trowel with a 1 layer of Portland cement mortar, laid in uniform squares, in every respect similar to the plaster on top of granolithic pavement. The dimensions of the squares were 5 times 5 ft. Their purpose was to take up expansion and contraction in the coating. During the year 1903, there were laid 9,056 SQ, IDs, of the waterproofing described. The labor cost of placing the 2 layers of felt and the 3 coats of pitch was as follows. 206 days' labor at a cost of $498, or an average of $2. 41 per day for the 9,056 SQ, IDs, which is equivalent to 5.5 CTS per SQ/YD, for labor. Since this is for 2 layers of felt, the labor cost was 2 3/4 CTS per SQ/YD of single layer. The labor cost of mixing and placing the 1 mortar covering was as follows. It required 589 days at a cost of $1,306, or an average of $2. 22 per day to place 9,056 SQ, IDs, which is equivalent to 14.5 CTS per SQ/YD. The total cost of labor for 2 layers of tar felt and the layer of cement mortar was, therefore, 20 CTS per SQ/YD. New York Rapid Transit Subway. The waterproofing consisted of alternate layers of asbestos felt and asphalt laid on the concrete and covered with concrete. A coat of hot asphalt was laid on the concrete, and on this a layer of felt, then another coat of asphalt and another layer of felt, and so on until the required number of layers of felt, from 2 to 6, were laid with asphalt between and on top and bottom. Natural asphalt containing not less than 95% bitumen was specified. The felt was required to weigh 10 pounds per 100 SQ, FT. In constructing sidewalls, the alternative was allowed of placing the waterproofing layer between a 4-in outside wall of brick laid in asphalt and the concrete lining. On 2 sections of the work, the actual cost of waterproofing was as follows: 98,074 SQ. IDS. Single-ply felt per SQ, YD. Labor laying $0, 05 materials and plant 0, 10, total $0, 15 1,337 Cu, IDS, brick and asphalt per Cu, YD. Labor laying $6, 32 materials and plant 11, 48, total $17. 253 Lonesome Valley Viaduct, 256 Railway Bridge, 106 methods of bridges over city streets, 253 Illinois, and Mississippi Canal, 196. 197 Lonesome Valley Viaduct, 254. 255 Railway Bridge, 105. 250 Summary of 230 aggregates balanced. Value of 14 broken stone, 13 cinders, 14 cost of 15 gravel, 14 heating. See heating aggregates. Kinds used 13 measuring. Methods of 42 open box 42. 50 trump automatic measurer 44 quantities in concrete. Test determinations 192 screened or crusher run. Stone for 15 sizes used 15 slag 14 voids in 25 weighing. Apparatus for 102 aqueduct construction cost of Cedar Grove Reservoir 549. 550 Salt River irrigation work. 540 methods of cast pipe Swansea, England. 584 Cedar Grove Reservoir. 545 Jersey City Water Supply. 544 Salt River irrigation works. 538 Torresdale filters. 540 asphalt concrete definition of 108 furnace. For heating 109. 110 machine mixing of 111 asphalt concrete construction cost of base. For mill floor 110. 111 slope paving for dam. 109 methods of base for mill floor. Slope paving for dam 108. 109 B bags, C cement bags. Depositing concrete under water 89, 90 barrels, C cement barrels. Belt conveyors capacity of 65 gas works foundations, Astoria N. 80 index. Abutment construction cost of bridges over city streets 254 Ernst, Cent, Bridge, Cincinnati, O. 257 Kansas City Outer Belt and Electric Rye. Y. 64 horsepower required 65 bench monuments construction of 656 cost of 657 blasting concrete 655 bonding new concrete to old 659 breakwater construction cost of Buffalo N. Y. 214 Marquette Mitch 209 212 methods of Buffalo N. Y. 212, 214 Marquette Mitch, 208, 212 bridge centers, C centers. Bridge construction cost of Arch Viaduct 373 Connecticut Ave. Bridge 392, 397 Elcott, Ind. Arch 398 5 Span Arch 407 Girder Highway 377, 379 Grand Rapids Bridge 410, 413 Molded Slab Girders 387 Plainwell, Mitch. Arch 399 Railway Bridge 375 Methods of Connecticut Ave. Bridge 387 Elcott, Ind. Arch 397 5 Span Arch 400 Girder Highway 367 377 Grand Rapids, Mitch. Arch 407 Molded Slab Girders 384 Plainwell, Mitch. Arch 398 Bridge Pier Construction Cost of Calf Killer River Bridge 243 245 City Island Bridge 236 Miami River Bridge 257 Steel Cylinder 241 Viaducts Cincinnati O 258 Williamsburg Bridge 230 231 Methods of Calf Killer River Bridge 241 245 City Island Bridge 235 K C, M, and O. Rye, 245, 250, 106, 107 Williamsburg Bridge, 237, 241 Broken Stone Crushing, C. Stone Crushing, Quarrying, C. Quarrying, Rocks for Best 13 Shoveling, C. Shoveling, Screened or Crusher Run 15 Voids in amount of 29, 30 Effect of granulometric composition, 30 Effect of hauling, 33, 34 Effect of loading, 29 Variation. Causes of 28, weight no index, 32 weight of 32, 33 Building construction cost of 4-story garage, 510 wall columns for power station, 490 walls for factory building, 507 divisions of work, 433 methods of 4-story garage, 509, 1-story car barn, 495, 6-story building, 491 wall columns, 488 walls for factory building, 505 C cableways capacity of 64 construction of bridge work, 369 cost of 64 fortification work, 186 retaining wall work, 269 cars mixer, charging 72 carts. C. Concrete carts, horse carts. Cement classification of 1 natural definition of 2 Portland. Definition of 1 quantity in concrete formula for computing 37 rule, for figuring 40 tables showing 39, 40. 41 quantity in mortar formula for computing 36 tables showing 38 test determinations 40. 41 theory of 35 shrinkage by wetting 35 slag. Definition of 2 weight 2. 4 cement bags capacity of 2. Packing for shipment 3 rebate on 3 storage house for 3 cement barrels capacity of 2. 3. 4 dimensions of 4 cement specifications, 4 cement testing. Cost of 4 centers computation of Luton Arch 566. Construction of conditions governing 363 Cocket. 50 FT. Lonesome Valley Viaduct 254. 255 Miami River Bridge 256, Nova Scotia Railways 108 Railway Bridge 231, 235 Scottish Railways 107, 108 Summary of 230 Tharsis and Calamas Rye. Span 364 Connecticut Ave. Bridge 392 5. Span Arch 400 Grand Rapids, Bridge 408 Luton Arch 365, Mechanicsville Bridge 365, Parabolic Arch 366 supported, 50 FT. Span 364, Walnut Lane Bridge 368, cost of Connecticut Ave. Bridge 392, 393 deflection of test determinations, 367 types of 363 charging barrows ransom. Description 71 sterling. Description 71 charging buckets wheeled 74 charging mixer cost of 270. 272 gravity from bins 69 methods of car plants 72 charging barrows 71 derricks and buckets 73 elevating charging hoppers 70 enumeration 68 gravity from bins 68 69 shoveling 72 73 wheelbarrows 70 wheeled bucket for 74 chutes cement bag. Construction of 65 concrete. Examples of 66, 67, 68 working gradient 65, 66 cinders 15 cofferdam construction cost of bridge pier 232 coloring concrete. Recipes for 666 colors for mortar. Recipes for 666 concrete asphalt. See asphalt concrete. Definition of one depositing, see depositing concrete. Mixes, see mixes. Mixing, see mixing concrete. Proportioning. Methods of 25 concrete bucket side, dumping 486 subaqueous cyclopean 87, O'Rourke 86, Stubner 88, concrete block molding. See molding concrete blocks. Sling for handling 216 concrete cars lock work. Coosa River 195 concrete carts hand. Capacity of 53, 54 horse. Briggs 298 ransom two-wheeled 53 culvert construction characteristics of 414 cost of arch 26 ft. Span 425 arch N. C. And St. L. Rye 418, 419, 422 Kalamazoo, Mitch. 430 Kansas City out of belt and electric Rye. 252 Pennsylvania 424 methods of arch N, C and St. L. Rye 417 arch Wabash Rye. 422 box C, B and Q. 414 Kalamazoo Mitch. 427 Pennsylvania 423 curb and gutter construction cost of Champaign, Ill. 326 estimating 321 Ottawa. Ont. 324 methods of Champaign, Ill. 325. 208. 209 pier construction, 222 characteristics of 86 closed buckets 86. 87. 88 Tremy Charlestown Bridge Foundations 92. 93 Masonry Bridge Foundations. France 93. 94 Harvard Bridge Foundations 91 Nussdorf Lock Foundations 94. 95 Drilling concrete. Drill mounting for 653 dumping concrete cost of wheelbarrows 55 methods of chutes. 55 wheelbarrows 55 dump wagons. For transporting concrete 54 efflorescence causes of 126 preventing. Methods of 126. 127 removing. Cost of 127 ejectors for washing sand. 7 erecting derrick cost of bridge pier 232. Erecting forms derrick. For 501 directions for building work 460 erecting molded columns. Cost of 520 methods of 520 erecting molded roof slabs cost of 522. Excavating cofferdams cost of 232. 244. 250 F fabricating reinforcement bending machine. For 468 bending tables. For for 466 methods of building work, 464 5-span arch bridge, 402 falseworks, inform construction, 144 finishing concrete surfaces methods of acid etching, and washing, 133 careful mixing, and placing concrete, 125, 126 coloring, 135 form construction, 124, 125 grout washing, 130 mortar facing, 128, 129 plastering, 128 scrubbing and washing, 131, 132, 133, 134 spading and troweling, 127, 128 special facing mixtures, 130 stuccoing, 128 tooling, 133, 134 washed gravel or pebble, 134 form construction cost of aqueduct, Cedar Grove Reservoir, 550 arch culverts, 418, 419, 422, 425, 430 battery emplacement, 188 bridge abutment, 257 bridge, 233, 235, 250 bridge pier work, 243 building work, 493, 496, 501, 503, 507, 511 Connecticut Ave. General discussion, 321 kinds of 318 Ottawa, Ont. 321 curbing, wood for shafts, 160, 161 D dam construction cost of Hemet, 104 Richmond, Ind. 224 Rock Island, Ill. 225 Spear Falls, 103 methods of Barossa Dam, 101 Boonton, N. J. Dam, 103 Boyd's Corner Dam, 105 Chaudière Falls, Quebec. 228 Chattahoochee River Dam, 100 Hemet Dam, 103, 104 McCall Ferry, Pa. 225, 228 Richmond, Ind. 223 Rock Island, Ill. 224, 225 Spear Falls Dam, 103 Water Works Reservoir, 104 Depositing Concrete Subaqueous Bags Bridge Foundations, 91 Marquette Breakwater, 209, 210 Peterhead Pier, 89, 90 Buckets Marquette Breakwater. Bridge 392, 393 Dam Rock Island, Ill. 225 Effect of design on 137 estimating. Method of 146, 147, 148, 149 Girder for separate casting, 517 Girder Highway Bridge 377, 380, 382 Grand Rapids Bridge, 412 God Lock, Ill, and Miss. Canal 201 Gun Emplacements, 185 Lock, Coosa River 196 Lock, Ill, and Miss. Canal 202, 206, 207 Mortar Battery Platform, 187 Permanent Way Structures, 252 Piers. For Taintor Gates, 198 Pier Superior Entry. Wise. 222 Reservoir for Fire Protection, 591, 592, 593 Retaining Walls, 273, 275 Retaining Wall Work, 270, 272 Slab, and I-beam floors, 450 subway lining, 362 economics of 136 falseworks, and bracing 144, 145 methods of aqueduct. Cedar Grove Reservoir, 546 aqueduct Torresdale filters, 541 arch culvert, 427 arch culverts, 421 blocks for Lake Pier, 216 blocks, molded under water 217. To 219 box culverts, 417 bridge piers, 255 building work, 492, 495 cement pipe molded in place, 577 circular columns, 445 columns, 434 Connecticut Ave. Bridge 392, coping for walls, 264 culvert pipe, 431 curb and gutter, 319, 321, 323 dam abutments, 196 dam, Rock Island, Ill, 228 5-span arch bridge, 400 Gasholder tank, 612 girder for separate casting, 516 guard lock, Ill, and Miss. Canal 200 lock, Coosa River 195 lock, Ill, and Miss. Canal 201, 203, 572 sidewalks, 309 six-story building, 492 slab and girder floors, 450, 456, 492 slab, and I-beam floors, 448, 450 slab girders, 385 steel, for conduits 533 steel. McCall Ferry Dam 227, 228 steel sheathed collapsible for conduits, 533 tunnel centers, 335, 341, 352, 358 tunnel sidewalls, 330, 335, 340, 351, 358 wall, 456, 460, 505 wall columns for factory, 498 computation. Methods of 140, 141 design considerations in 141 details entering 142, 143 lubrication. Methods of 144 lumber dressing. Purpose of 138 finish and dimensions 138. 139 kinds suitable, 138 mortar, facing 129 pile round, 179 rectangular pier. Cost of. Rule for calculating 14 removing. Time of. Directions for 145, 146 unit construction. Purposes of 143 steel. Opportunity for development 136 fortification construction. Cost of battery emplacement 188, 189, 190 gun emplacements, 185 mortar battery platform, 187 methods of battery emplacement, 187, 189 gun emplacements, 185 mortar battery platform, 186 foundation construction street railway. Cost of continuous mixer 301 methods of continuous mixer 300, 301 freezing weather. Laying concrete in 112 G grain elevator bins construction. Methods of 635, gravel characteristics of 14 commercial sizes of 22 screening and washing plants 23 screening. C screening gravel. Voids in amount of 30. 31 effect of granulometric composition 29, 30 weight no index 32 amount of 31, 32 grouting underwater hermitage breakwater 96 tests of efficiency of 95 H heating, aggregates efficiency of 114 methods of bridge work, Plano, Ill, Manhole Hartford, Con. 536 Marquette breakwater 211, 212 ornamental columns 446, 447 piers for Taintor gates 198 polygonal columns 443, 444 rectangular columns 435, 443, 490, 492, 511 Reservoir Bloomington, Ill. 605 Reservoir Ft. Meade, S. DAC, 600 Retaining Wall C, B, and Q, RR 262 Retaining Wall, Chicago Drainage Canal 275 Retaining Wall, Grand Central Terminal 281 Retaining Walls N, Y, C, and H. 261, 262 Salt River Aqueduct 539 Sewer, Cleveland, O. 564 Sewer Invert, Haverhill, Mass. 554 Sewer Invert, Medford, Mass. 535 Sewer Invert, Middlesborough, Chi. 561 Sewer South Bend, Ind. 551 Sewer Wilmington, Dell. 118 Chicago, Burlington, and Quincy, RR. 118 Hot Water Tanks 120 Huronian Power Co. S. Dam Work 118 Portable Combination Heater 115 Stationary Bin Outfits 115 116 Steam Box 119 Steam Jets 119 Wachusett Dam Work 117 Water Power Plant, Billings, Mont. 116, 117 Hoists Gallows, Frame and Horse 54 Ransom 476 Wallace Lindismith 474 Housing Concrete Work Methods of Chicago, Burlington, and Quincy, 119 Dam. Chaudière Falls, Quebec 120. 121 Portable Unit System for Buildings 122. 123 I inclines grades of 62L laying concrete blocks cost of 526. 529 loading concrete characteristic features 53 rate of 53 loading materials cost of shoveling into wheelbarrows 47 rate of 6 lock construction cost of Coosa River 196 ill. And Miss. Canal 200, 202, 205, 207 Cascades Canal 190, 191, 192, 193 Coosa River 194, 195 ill. And Miss. Canal 200, 207 Lock Foundation 207 M Manhole Construction Cost of Rye, N, Y. 577 Methods of Rye, N, Y. 576 Mixes Batch Chicago 662 Chicago Improved Cube 75 661 Crop 661 Forms of 75 Cowring 662 Polygon 663 Ransom 75 661 Rate of Output 83 84 Smith 77 662 Snell 660 Charging C charging mixers. Continuous Advanced 660 Eureka Automatic Feed 78 660 Forms of 78 foot 297 Schaeffler 660 Efficiency of Rating. Methods of 84 85 Gravity Forms of 79 Gilbreth Trough 80 Haynes. Fixed Hopper 80 81 Haynes. Telescoping Hopper 81 Output Conditions affecting 83. 84 Haynes Gravity 83 Types of 74 Mixing Concrete Hand Cost of Abutment Construction 197 Culvert Work 428 430 Fortification Work 189 Girder Highway Bridge 380 382 lock. Cascades Canal 192 Marquette breakwater. 209, 210, 212 retaining wall. Allegheny 284 superintendents. 57, 58 cost of 52, 59 methods of abutment construction 196, 197 examples from practice. 49 fortification work, 189 lock foundation, 207 Marquette breakwater, 209 retaining wall, Allegheny 283, 284 rates of 50, 51, 52 specific directions, necessity, 51, 52 machine cost of 361, 362, 518 Buffalo breakwater, 214 building work, 504, 507, 511 dam work Rock Island, Ill. 225 fortification work, 190 Haynes gravity mixer, 83 lock, Cascades Canal, 193 lock, Ill. And Miss. Canal 206, 207 pier, superior entry wise. 222 retaining wall, Allegheny, 284 retaining wall work, 270, 273, 275 methods of bridge abutment work, 253, 254 building work, 471 fortification work, 189 Haynes gravity mixer, 82, 83 operations enumerated, 61 piers in caissons, 165, 166 mixing plants construction battery emplacement, 187, 188 bridge construction, 369, 371, 372, 374, 386, 389, 403. Culvert work, 415, 416, 418, 420, 422, 423 dam, McCall Ferry, Pa. 226 lock, Cascades Canal, 190, 191 lock work, Coosa River, 194 lock work, Ill. And Miss. Canal, 198, 199, 204 pier work, Superior wise. 221 retaining wall, Grand Central Terminal, 277 scow, Port Colborne Harbor, 216, 217 traveling, Chaudiere Falls Dam, 228 traveling, Chicago track elevation, 267 traveling, Galveston Sea Wall, 268 cost of lock work, Ill. And Miss. Canal, 199 retaining walls, Chicago Drainage Canal, 274 mixing water reducing freezing point methods of 112 salt, sodium chloride, 113 solutions for composition of 113 molding blocks cost of 524, 528, 530, 531 Marquette breakwater, 211 Connecticut Ave. Bridge 395 separate casting, 519 methods of 523, 526 Connecticut Ave. Bridge 393 Marquette breakwater, 211 pier Port Colborne Harbor, 215 separate casting, 513, 515 molding cement pipe cost of Irrigan, or 584 ransom mold, 577, 579 methods of Irrigan, or 581 ransom mold, 577 molding culvert pipe cost of chic, and N-il-ah-ah, 432 methods of chic, and N-il-ah-ah, 430 molding girders cost of separate casting, 519 methods of separate casting, 513, 514, 515 molding piles forms for C forms, methods of corrugated polygonal, 176 round, 179 plant arrangements for 169 cost of 522 molding roof slabs methods of 521 mortar facing cost of lock, ill. Miss Canal 206 forms for 129 N natural cement, C cement. O ornament construction methods of iron molds, 644 molding in place, 647 plaster molds, 646 sand molding, 644 wooden molds, 637 P pavement base construction cost of batch mixer, 306 batch mixer and wagon haulage, 302 brick, champagne, ill. 296 continuous mixers, 298, 300, 305 miscellaneous examples, 294, 295, 296 New Orleans, 293 stone block, New York, 292 Toronto, Ont, 293 traction mixer, 304 methods of batch mixer, 305 batch mixer, and wagon haulage 302, continuous mixers 297 to 300, 304 hand mixing 290 machine mixing 290, 291 traction mixer 303 mixtures, employed 288 organization, for 288 stock pile distribution 289. A cost of ocean pier 173. 174 Raymond process 152. 154. 155 methods of building foundation work 174. 175. 178. 179 compressed process 158, 159 enumeration of 151 molding in forms 161 to 170, 172, 179, 180 molding in place 151 Ocean Pier 172, 173 Raymond process, 152 rolling process, 181 simplex process, 155, 156, 157 spread footing process, 157, 158 track scales, 181 pile driving conditions, requisite for cost of Ocean Pier 173. 174 methods of corrugated polygonal 177, 178, hammer 179, 180, 181 water jetting 172, 177 pile driving caps 177, 178, 180 pile rolling machine 182 piles. C molding piles. Construction compressor process 158, 159 octagonal 180 rolling process, 181 round piles 178, 179 spread footing process 157, 158 square 179, 180 cost of rolling process 183 driving, C pile driving, handling, sling for 175 Raymond construction, method of 151, 152 cost of 152, 154, 155 simplex construction, methods of 155, 156. 157. Placing concrete, cost of bags. Underwater 210. Belt conveyors 275. Buckets underwater 209. Buffalo breakwater 214. Car and trestle plant 196. 201. 202. 206. 207. 244,280. 422 cars and chute 193 cars and derrick 285 derricks 192. 233. 235 Port Colborne Harbor 217 pneumatic caissons 230 retaining wall work 270. 272 Steel cylinder pier 241 subaqueous buckets 223 wheelbarrows 189. 197. 198. 257. 285. 418. 419. 423 methods of building work 486 locks Coosa River 194 pneumatic caissons 237. 238 retaining wall work 266 sewer work 537 placing reinforcement cost of building work 494 directions for 470 permanent way structures 252 pole base cost of 658 Portland cement C cement proportioning concrete C concrete Q quarrying cost of limestone 18. 276 trap rock 17 methods of limestone 18 trap rock 17 are ramming concrete. See also placing concrete. Cost of 423 conditions governing 56 examples from practice 56. 57 pavement base 292. 294 methods of piers. Lonesome Valley Viaduct 255 specific directions. Necessity of 57 Raymond piles. C piles, reinforcement. Weight in concrete tables for estimating. 663 to 665 removing forms derrick for. 502 methods of building work. 461 time for building work. 462 reservoir construction cost of covered for fire protection. 594. 595 FT. Pavement construction cost of fortification work 186 Richmond, Ind. 318 Windsor, Ont. 317 methods of Richmond, Ind. 318 Windsor, Ont. 316 pier construction cost of Lonesome Valley Viaduct 255 Superior Entry, Wise. 222. 223 Taintor Gates 198 methods of Port Colborne Harbor 215 to 217 Superior Entry, Wise. 217 to 223 piers in caissons construction of methods of 159 to 168 cost of 168. 169 pile construction. See molding piles, pile driving. Mead, S. DAC. 601 methods of Bloomington, Ill. 603 covered for fire protection. 588 Fort Meade, S. DAC. 597 reservoir lining cost of Canton, Ill. 629 Chelsea, Mass. 623 Jerome Park. 628 Pittsburgh, Pa. 630 Quincy, Mass. 619 methods of Chelsea, Mass. 620 Jerome Park. 628 Quincy, Mass. 617 reservoir roof. Cost of 632 retaining wall construction cost of 286 Chicago drainage canal, 273 to 277 footing for masonry, 283 Grand Central Terminal, 280 Railway Yard, 282 Methods of Allegheny Track Elevation, 283 Chicago Drainage Canal, 272 to 277 Grand Central Terminal, 277 to 281 Subway and Trench, 269, 270 Retaining Walls Comparison of Plain and Reinforced, 260, 261 Types of 259 Rubble Concrete Construction, Cement Saving in 98 Cost of Abutment, Railway Bridge, 106 Hemet Dam, 104 Spear Falls Dam, 103 Economy, Limitations to 98, 99 Methods of Abutment, Railway Bridge, 105 Barossa Dam, 101 Boonton Dam, 103 Bridge Piers, Nova Scotia, 108 Bridge Piers, Scotland, 107, 108 Bridge Piers, Spain, 106, 107 Chattahoochee River Dam, 100 Dams for Waterworks, 104, 105 Hemet Dam, 103, 104 Spear Falls Dam, 103 Percentages Rubble Stone, 100, 101, 103, 105, 108 Shape of Stones for 99 Runway Construction, Methods of 48 Salt Percentages in Mixing Water, 114 Sand Balanced, Value of 6 Cleanness, Value of 5 Cost of Excavating and Loading, 6 Granulometric Composition, 28 Prices Charged for, 6 Sharpness, Value of 5 Substitutes for 5 Voids in amount of 26, 28 Conditions Affecting, 25 Effect of Moisture, 25 Effect of Size of Grains, 27 Volume in Concrete, 5 Weight of 6, 26 Sand Washing Cost of Ejector Method, 10 Hose Method, 7 Tank Method, 13 Methods of Ejectors, 7 Hose, 7 Tank, 10 Rate of Ejector Method, 9 Hose Method, 7 Tank Method, 10, 12, 13 Water Required Ejector Method, 9 Sand Washing Plants, 7 to 13 Screening Gravel Cost of L. S and M. S. Rye, 22 Stewart Peck Sand Co., 24 Methods of Handwork, 19 Lock, Cascades Canal, 191 Scraper into Wagons, 21 Stewart Peck Sand Co., 23 Sewer Construction Cost of Cleveland O., 566 Coldwater Mitch, 574 Haverhill, Mass., 557 Medford, Mass., 535 Middlesborough, Chi., 562 St. Louis, Mo., 560, 561 South Bend, Ind., 554 Wilmington, Dell., 571, 573 Methods of Cleveland, O., 563 Coldwater, Mitch, 573 Haverhill, Mass., 554 Medford, Mass., 535 Middlesborough, Chi., 561 Pipe, St. Joseph, Mo., 579 St. Louis, Mo., 558 South Bend, Ind., 551 Wilmington, Dell., 569 Shoveling Cost of Concrete into Barrows, 197 Rate of Broken Stone from Piles, 46 Broken Stone from Shoveling Boards, 46 Broken Stone from Cars, 45 Gravel against Screens, 21 Sand into Wheelbarrows, 46 Shoveling Boards Wooden, for Broken Stone, 46 Sidewalk Construction Cost of Estimation of 311, 312 Quincy, Mass., 314 San Francisco, Cal., 315 Toronto, Ont., 313 Methods of Bonding Wearing Surface to Base, 310 Edger for 310 General Discussion, 307 Points for 310 Prevention of Cracks, 311 Protection from Weather, 311 Quincy, Mass. 314 Toronto, Ont. 313 San Francisco, Cal. 314 silo construction cost of 632 methods of 631 slag 14 slag cement C cement specific gravity stone various 33 spreading concrete cost of 197 effective method of dumping on 55 standpipe construction cost of Attleboro, Mass. 611 methods of Attleboro, Mass. 609 stockpiles capacity of 46 distribution pavement work 289 purposes of 45 stone specific gravity 33 stone crushing cost of cobblestone 20 limestone 18 225 273 276 trap rock 17 methods of cobblestone 19 limestone 18 trap rock 17 stone crushing plant construction lock work ill and miss canal 200 stone dust value for mortar 5 storing materials cost of 185 225 subway lining cost of Long Island 361 New York Rapid Transit Rye 357 358 methods of Long Island 361 New York Rapid Transit Rye 356 superintendent's cost of 57 58 185 193 197 210 211 212 273 275 397 T tamping concrete cost of 197 lock ill and miss canal 206 207 method of lock ill and miss canal 204 tank construction methods of gas holder Des Moines, Iowa 609 gas holder New York 614 tooling concrete cost of 394 396 transporting concrete cost of cableways 270 cars 280 chutes 67 cars and derricks 285 car and trestle plant 63 210 212 222 wheelbarrows 53 189 197 272 285 293 294 296 methods of belt conveyors see also belt conveyors 64 to 65 bucket hoists 474 building work 472 cableways 64 186 289 369 370 cars 404 421 cars and chute 191 192 car and trestle 63 243 246 377 chutes see also chutes 66, 67, 68 derricks, 479 dump wagons, 54 effect on placing, 54 enumeration of 52 hand costs, 53 hoist and cars, 372 platform hoists, 479 pulley and horse, 489 traveling derrick plant, 374 trestle runways, 54 wheelbarrows, 53 transporting materials cars for 45 cost of bridge pier work, 243 cars, 275 car and trestle plant, 222 dam, Rock Island, ill, 225 horse carts, 49, 270, 273 lock, ill, and miss, canal, 206, 207 wheelbarrows, 47, 48, 189, 197, 214, 280, 292, 293, 294, 296, 419 methods of belt conveyors. See also belt conveyors. 64 to 65 cableways, 64. 269 carrying in shovels, 47 chutes. See also chutes. 46, 65, 66 hand carts. 48 horse carts, 48 Indians, 62 shoveling to derrick buckets, 46 trestle and car plants, 63 wheelbarrows, 47 trestle runways. Cost of 54, 55 trestles car. Cost of 63 structural details, 63 tunnel construction. See tunnel lining. Tunnel lining backfilling machine for 330. Cost of Cascade Tunnel 338, Gunnison Tunnel 355, Hodges Pass Tunnel 345, Mullen Tunnel 333, Peekskill Tunnel 336, Short Railway 344, Methods of Burton Tunnel 347, Capitol Hill, Washington, D.C. 329, Cascade Tunnel 336, General Discussion 328, Gunnison Tunnel 353, Hodges Pass Tunnel 338, Mullen Tunnel 332, Peekskill, N. Y. 333, Mortar Car for 333, Removing Old. Methods of 332, Traveling Derrick for 330, Traveling Platform for 337. 350 U Unloading Materials, Cost of Grab Buckets, 62 Methods of Grab Buckets, 62 V Voids. See also gravel, sand, stone, conditions governing 25 W wall ties, construction of 265 washing gravel, cost of L. S. and M. S. Rye. 22 Stewart Peck Sand Co. 24 Washing gravel methods of Lock, Cascades Canal 191 Stewart Peck Sand Co. 23 Water quantity in concrete rule for figuring 42 waterproofing, cost of hydrolithic coating 677 Long Island Subway 679 New York Subway 680 Sylvester Mortar 675 Sylvester Wash 674 Methods of bituminous coatings 670 Covered reservoir for fire service 596, hydrolithic coating 676, impervious mixtures 668 Long Island Subway 678 Medusa compound 669 moisture coatings 677 New York Subway 679 Novoid compound 670 oil and paraffin washes 677, Star Stellan cement 669, Sylvester mortar 675, Sylvester wash 673, Cherelmy wash 673, wheelbarrows loads for 47 updated editions will replace the previous one. The old editions will be renamed, creating the works from print editions not protected by U.S. Copyright law means that no one owns a United States copyright in these works, so the Foundation and you can copy and distribute it in the United States without permission and without paying copyright royalties. Special rules set forth in the general terms of use part of this license apply to copying and distributing project and may not be used if you charge for an e-book, except by following the terms of the trademark license, including paying royalties for use copies of this e-book. Complying with the trademark license is very easy. You may use this e-book for nearly any purpose, such as creation of derivative works, reports, performances, and research. Project Gutenberg e-books may be modified and printed and given away. You may do practically anything in the United States with e-books not protected by U.S. copyright law. Redistribution is subject to the trademark license, especially commercial redistribution. Start full license. Please read this before you distribute or use this work. Distribution of electronic works by using or distributing this work or any other work associated in any way with the phrase Project Gutenberg. You agree to comply with all the terms of the full www. Gutenberg. org/license. Electronic works. Electronic work. You indicate that you have read, understand, agree to, and accept all the terms of this license and intellectual property, trademark/copyright agreement. If you do not agree to abide by all the terms of this agreement, you must cease using and return or possession. If you paid a fee for obtaining a copy of or access to by the terms of this agreement, you may obtain a refund from the person or entity to whom you paid the fee as set forth in paragraph 1. 8. Used on or associated in any way with an electronic work by people who agree to be bound by the terms of this agreement. There are a few, even without complying with the full terms of this agreement. See paragraph 1. See below. There are a lot of things you can do with Project Gutenberg electronic works if you follow the terms of this electronic works. See paragraph 1. Below. Foundation or PGLAF owns a compilation copyright in the collection. Works in the collection are in the public domain in the United States. If an individual work is unprotected by copyright law in the United States and you are located in the United States, we do not claim a right to prevent you from copying, distributing, performing, displaying, or creating derivative works based on the work as long as works in compliance with the terms of this agreement. For keeping the comply with the terms of this agreement by keeping this work in the you share it without charge with others. 1. D. The copyright laws of the place where you are located also govern what you can do with this work. Copyright laws in most countries are in a constant state of change. If you are outside the United States, check the laws of your country in addition to the terms of this agreement before downloading, copying, displaying, performing, distributing, or creating derivative works based on this work or any representations concerning the copyright status of any work in any country other than the United States. 1. 1. The following sentence with active links to or other performed, viewed, copied, or distributed. This e-book is for the use of anyone anywhere in the United States and most other parts of the world at no cost and with almost no restrictions whatsoever. You may copy it, give it away, or reuse it under the terms at www.gutenberg.org. If you are not located in the United States, you will have to check the laws of the country where you are located before using this e-book. Derived from texts not protected by U.S. copyright law does not contain a notice indicating that it is posted with permission of the copyright holder. The work can be copied and distributed to anyone in the United States without paying any fees or charges. If you are redistributing or providing access to a work with the phrase Project Gutenberg associated with or appearing on the work, you must comply either with the requirements of paragraphs 1. 1 through 1. 7 or trademark as set forth in paragraphs 1. 8 or 1, 9. With the permission of the copyright holder, your use and distribution must comply with both paragraphs 1. 1 through 1. 7 and any additional terms imposed by the copyright holder. Additional terms posted with the permission of the copyright holder found at the beginning of this work. License terms from this work or any files containing a part of this one. 5. Do not copy, display, perform, distribute, or redistribute this electronic work, or any part of this electronic work, without prominently displaying the sentence set forth in paragraph 1. One with active links or immediate access to the full terms of the Project Gutenberg license. 1E6. You may convert to and distribute this work in any binary, compressed, mocked up, non-proprietary or proprietary form, including any word processing or hypertext form. However, if you provide access other than plain vanilla ASCII or other format used in the official www. Gutenberg.org, you must, at no additional cost, fee, or expense to the user, provide a copy, a means of exporting a copy, or a means of obtaining a copy upon request of the work in its original plain vanilla ASCII or other form. Any alternate format must include the 1E7. Do not charge a fee for access to, viewing, displaying unless you comply with paragraph 1E8 or 1E9. 1E8. You may charge a reasonable fee for copies of or provided that you pay a royalty fee of 20% of the gross profits you derive from you already used to calculate your applicable taxes. The fee is owed agreed to donate royalties under this paragraph to the Project Gutenberg Literary Archive Foundation. Royalty payments must be paid within 60 days following each date on which you prepare, or are legally required to prepare, your periodic tax returns. Royalty payments should be clearly marked as such and sent to the Project Gutenberg Literary Archive Foundation at the address specified in Literary Archive Foundation. You provide a full refund of any money paid by a user who notifies you in writing or by email within 30 days of receipt that S/he license. You must require such a user to return or destroy all copies of the works possessed in a physical medium and discontinue works you provide, in accordance with paragraph 1F3, a full refund of any money paid for a work or a replacement copy if a defect in the electronic work is discovered and reported to you within 90 days of receipt of the work. You comply with all other terms of this agreement for free. 1E9. If you wish to charge a fee or distribute a Project Gutenberg trademark electronic work or group of works on different terms than are set forth in this agreement, you must obtain permission in writing forth in section 3 below. 1F. Effort to identify, do copyright research on, transcribe and proofread works not protected by U.S. copyright law in creating the project electronic works, and the medium on which they may be stored, may contain defects, such as but not limited to incomplete, inaccurate, or corrupt data, transcription errors, a copyright or other intellectual property infringement, a defective or damaged disk or other medium, a computer virus or computer codes that damage or cannot be read by your equipment. 1F2. Limited warranty, disclaimer of damages except for the right of replacement or refund, described in paragraph 1F3, the Project Gutenberg Literary Archive Foundation, the owner of the Project Gutenberg trademark, and any other party distributing a Project Gutenberg trademark electronic work under this agreement, disclaim all liability to you for damages, costs, and expenses, including legal fees. You agree that you have no remedies for negligence, strict liability, breach of warranty, or breach of contract, except those provided in paragraph 1F3. You agree that the foundation, the trademark owner, and any distributor under this agreement will not be liable to you for actual, direct, indirect, consequential, punitive, or incidental damages, even if you give notice of the possibility of such damage. 1F3. Limited right of replacement or refund if you discover a defect in this electronic work within 90 days of receiving it. You can receive a refund of the money, if any. You paid for it by sending a written explanation to the person you received the work from. If you received the work on a physical medium, you must return the medium with your written explanation. The person or entity that provided you with the defective work may elect to provide a replacement copy in lieu of a refund. If you receive the work electronically, the person or entity providing it to you may choose to give you a second opportunity to receive the work electronically in lieu of a refund. If the second copy is also defective, you may demand a refund in writing without further opportunities to fix the problem. 1. F4. Except for the limited right of replacement or refund set forth in paragraph 1. F3. This work is provided to you as is, with no other warranties of any kind, express or implied, including but not limited to warranties of merchantability or fitness for any purpose. 1. F. 5. Some states do not allow disclaimers of certain implied warranties, or the exclusion or limitation of certain types of damages. If any disclaimer or limitation set forth in this agreement violates the law of the state applicable to this agreement, the agreement shall be interpreted to make the maximum disclaimer or limitation permitted by the applicable state law. The invalidity or unenforceability of any provision of this agreement shall not void the remaining provisions. 1 F6. Indemnity. You agree to indemnify and hold the foundation, the trademark owner, any agent or employee of the foundation, anyone in accordance with this agreement, and any volunteers associated with the electronic works, harmless from all liability, costs and expenses, including legal fees, that arise directly or indirectly from any of the following which you do or cause to occur. A. Distribution of this defect you cause. Electronic works in formats readable by the widest variety of computers, including obsolete, old, middle-aged, and new computers. It exists because of the efforts of hundreds of volunteers and donations from people in all walks of life. Volunteers and financial support to provide volunteers with the remain freely available for generations to come. In 2001, the Project Gutenberg Literary Archive Foundation was created to provide a secure archive foundation, and how your efforts and donations can help. See sections 3 and 4. And the Foundation information page at www.gutenberg.org. 501 c. 3. Educational corporation organized under the laws of the state of Mississippi and granted tax-exempt status by the Internal Revenue Service. The Foundation's EIN or Federal Tax Identification Archive Foundation are tax-deductible to the full extent permitted by U.S. federal laws and your state's laws. The Foundation's business office is located at 41 Watchung Plaza, 516, Montclair, NJ 07042, USA, +1 862 621 to 9288. Email contact links and up-to-date contact information can be found at the Foundation's website and official page at www.gutenberg.org/contact Literary Archive Foundation public support and donations to carry out its mission of increasing the number of public domain and licensed works that can be freely distributed in machine-readable form accessible by the widest array of equipment, including outdated equipment. Many small donations, $1 to $5,000, are particularly important to maintaining tax-exempt status with the IRS. The Foundation is committed to complying with the laws regulating charities and charitable donations in all 50 states of the United States. Compliance requirements are not uniform, and it takes a considerable effort, much paperwork, and many fees to meet and keep up with these requirements. We do not solicit donations in locations where we have not received written confirmation of compliance. To send donations or determine the status of compliance for any particular state, visit www.gutenberg.org/donate. While we cannot and do not solicit contributions from states where we have not met the solicitation requirements, we know of no prohibition against accepting unsolicited donations from donors in such states who approach us with offers to donate. International donations are gratefully accepted, but we cannot make any statements concerning tax treatment of donations received from outside the United States. U.S. laws alone swamp our small staff. Methods and addresses. Donations are accepted in a number of other ways, including checks, online payments, and credit card donations. To donate, please visit www.gutenberg.org/donate. Professor Michael S. Hart was the originator of the Project Gutenberg concept of a library of electronic works that could be freely shared with anyone. For 40 years, he produced and volunteer support editions, all of which are confirmed as not protected by copyright in the U.S., unless a copyright notice is included. Thus, we do not necessarily keep e-books in compliance with any particular paper edition. Most people start at our website, which has the main PG search facility, www.gutenberg.org. Archive Foundation, how to help produce our new e-books, and how to subscribe to our email newsletter to hear about new e-books.